What up, what up? This video goes over the first three sections of AP Precalculus. Change in tandem, rates of change, and rates of change in linear and quadratic functions. So let's just jump right into it. Again, this is an AP Calculus concept, and this is following the AP standards found on College Board. If you have an AP class, your teacher is going in this order. The first thing we're going to talk about is concavity. Now, I know what you're thinking. Concavity? Well, I speak Spanish. Does that mean I need to go to the dentist? Concavity looks like this. It's basically curves. All right, and we have two types of concavity. This guy is called concave down. It's a bowl that's upside down. A very popular haircut nowadays called the Edgar kind of looks like this. We have another type of concavity. This is concave up. Now let's explore what we're dealing with here. With concavity, we see symmetry. So let's draw lines of symmetry straight down the middle of our concave down and our concave up. Now, what we have with concavity is we're pretending that we are on a skateboard, either going up a hill or going through like a half pipe or something like that. And while we're on our skateboard, if I were to start going up this hill, on concave down, and I start here, it represents like a positive slope. And as I go up the hill, I kind of flatten out. And then at one point, I kind of hit this peak, and then I start going down the hill like so. I'm not a fan of what I did here, so let me get rid of you and try to flatten you out like that. That's much better. Erase. Now, this is concave down. On the left side of concave down, we're noticing a few things. On the left side of concave down, my rate of change, so right off the bat, we're talking about rate of change. Now, remember, it's very important to understand that rate of change is the same thing as slope. So all of these slopes that I drew out here is also the same thing as rate of change. On the left side of concave down, my rate of change is positive. Every single time, my rate of change is positive. But this is what I'm noticing. As I'm moving from the left and to the right, my rate of change is flattening out. So if this is like a slope of up 3 over 1, and if this is like a slope of up 2 over 1, and that's a slope of up 1 over 1, and that's a slope of 0 at the tippy top, my rate of change is positive, but it's also decreasing. So those are two very important words. A rate of change being positive means it just looks like this. A rate of change is decreasing means that over time it's flattening out and going from positive to 0. Now, similarly, on the right side, I can look at my skateboard going down the hill. As it's at the very tippy top, it's 0. But the moment I move away from the tippy top, it's now a negative slope. So the rate of change on the right side of concave down is negative. On the right side of concave down, my rate of change is negative, but what I also see is that my 0 becomes like a negative 1. And then becomes like a negative 2, and then becomes a negative 3. So on the right side of concave down, my rate of change is negative, but it's also decreasing still. So what we've learned so far is that when my rate of change is decreasing, it's concave down no matter what. On the left side of concave down, it's a positive slope. It's a positive rate of change. My function is increasing. However, my rate of change is decreasing on concave down. Understand the difference between the two. My function is what is the graph doing. My rate of change is what is the slope doing. Huge difference. Now, if you're like, wow, sir, you really drew that too big and too close to concave up. I did it on purpose. And here's why. If I look at the left side of concave up, I am now a skateboarder going into a half pipe. So once I drop into the half pipe, I'm a steep negative slope, okay? And then it's still negative, but the moment I hit the very bottom, it's zero, it's flat. And then once I go up the hill, it's positive, some more. So on the left side of concave up, I have a negative slope, which means my rate of change is negative. However, on the left side of concave up, I go from like a slope of -4 to -3 to -2 to -1 to 0. My negatives are starting to approach 0, which means my rate of change for the left side of concave up is increasing. Ooh, that's different than what I've seen before. Okay. Now the right side of concave up, my rate of change went from negative, it hits the bottom, and then starts being positive. So on the right side, my rate of change is positive. On the right side, my rate of change is positive. However, what is my rate of change doing? Well, my slope, as I continue moving to the right, is a positive slope, steeper, positive, which means on the right side, my rate of change is increasing. So what we've learned here is that when it's concave down, the rate of change is decreasing. Okay, it starts going positive, then getting smaller. For concave up, it starts out at a very negative, steep slope, which means very negative, and then gets positive. Understand the difference between, oh, my function is decreasing, which means it's just going down. Okay, negative slope, versus my rate of change is decreasing, which means it's getting smaller. Big difference between the two. Now, the other thing we need to know about concavity is whenever we have a change in concavity, so right now I'm concave down and then boom, all of a sudden concave up, that change in concavity right there has a name, and it's called an inflection point. A change in concavity is called an inflection point. If it doesn't change from concave down to concave up, or if it doesn't change from concave up to concave down, then it's not an inflection point. Okay, if it's a straight line, it doesn't have concavity. Okay, so make sure we're understanding that concavity is this curvature. Okay, and we need to make sure that whenever we are given a visual, we understand the difference between something that's concave and something that's not. So that's concavity. Okay, that's thing number one that we need to look at. Thing number two that we need to look at is the average rate of change. Now, if I were to draw you a picture, okay, and, here's just a very typical graph. If I were to draw some curved line, looks something like this, right? In pre-calculus, we deal a lot with intervals. Okay, so interval means on the x-axis, I have a spot right here and a spot right here. What's happening in between? Okay, so let's call the first spot A on the x-axis. This is an x. And let's call the second spot B. Okay, on the y-axis, also known as the f of x axis, if I plug in A, I'm going to get this guy right here. So that lines up with f of A. If I plug in B, that lines up with this point right here on the line, which lines up with f of B. Now, rate of change, we mentioned a bunch of times in the last slide, is slope. The average rate of change is the exact concept. However, we view slope as a straight line. So the average rate of change is the straight line change between point A to point B. So if I can successfully draw this and not make it look stupid, an average rate of change is the straight line going from A to B. And so if I was looking at a graph, I should be able to count rise over run and figure out what my rate of change is. However, if I'm not given a graph, or if I need to show calculations, what I normally might do to find rate of change is give you the slope formula, which is this guy right here. However, in AP Precalculus, we rarely use the slope formula. Instead of x sub 1, y sub 1, we use the point A, f of A. And instead of x sub 2, y sub 2, we use the point B, f of B. So if I wanted to find the rise over run here, what I would do is do f of B minus f of A over B minus A. It's the same exact thing as the slope formula, but more AP Precalculus-y. Okay? Average rate of change. And again, the average rate of change gives me the slope, which gives me a rate from A to B if I'm dealing with a curved line. Okay? And even if I'm not dealing with a curved line, it does the same thing if it's linear. It's just not as useful. All right, let's talk about linear and quadratic rates of change. Now, a linear function, you know what that is. It's a perfectly straight line. A quadratic function is a parabola, which means things change. Okay, the patterns are not as exact as what they are for linear. And normally with these types of problems, you are going to be given some type of table or some type of chart of x or y values, but I'm going to use f of x because it just looks nicer. Okay, so I'm just literally making this up on the spot. This doesn't mean anything special. The fact that I started at -2 means absolutely nothing. And I'm going to do -4, -2, -1, -1 again, -2, -4. All right, now, you probably learned back in Algebra 1 or 8th grade math that if it's linear, that your pattern, as long as these guys go up by the same number, your pattern over here is going to do the same exact thing. Now, AP Precalculus uses an absolutely terrible phrase that I'm going to try to pull out of a hat, and I believe it's called consecutive input value equal interval stuff. Okay, and when you see that phrase, consecutive input values equal interval, I think it's actually consecutive equal interval input values. I think I nailed that. What that means is x going up by the same number every time? Yes, which means they're consecutive equal interval input values. Terrible, but that's what that means. So over here, x is going up by 1 every time. So if it's linear, whatever is happening over here has to happen the same every single time. So let's test its linearity, if that's even a word. To get from -4 to 2, I add 2. To get from -2 to -1, I add 1. To get from -1 to -1, I do nothing. To get from -1 to -2, I subtract 1. To get from -2 to -4, I subtract 2. Now, is this the same exact number every single time? No, then it's not linear. So now if we're going to test how quadratic it is, we're going to do the same exact thing with these numbers. How do we get from 2 to 1? Subtract 1. How do we get from 1 to 0? Subtract 1. How do we get from 0 to -1? Subtract 1. How do we get from -1 to -2? Subtract 1. So what this -1 means, right, is if I wanted to find a pattern here, then every time I bump up to the next output value, I just subtract 1 more. I add -1 more. So the next guy, I'm going to go from -4, I'm going to subtract 3 to that. And I'm going to go for whatever that number is and subtract 4 from that, and so on and so forth. Okay, but what we got here, since the number for quadratic was the same throughout the whole time, we have ourselves a quadratic. And the way you would see that in an AP exam is, which of these statements is true? And the solution would be, this is quadratic because the consecutive equal interval input values of the rate of change of the rate of change. So here's your regular rate of change. So this would be considered the rate of change of the rate of change is the same. The verbiage is terrible. That's what makes this an AP exam. Okay, rate of change of the rate of change. Actually, I think they say rate of change of the rates of change. I'm a math person for a reason. Words are not my thing. So let's just do a bunch of examples and see what we got. Okay, let's take all of that wonderful knowledge and answer some questions. I made all of these up. So the validity of, if you're wondering, well, am I going to see this exact same problem on an AP exam? No, but these are the types of problems that you see on like AP Classroom. These are the types of problems that you see from practice exams that College Board makes. This is what you would see. I just pulled a bunch of pictures from the internet and created my own problems based off of those pictures. So A, on which interval or intervals is the rate of change increasing? We know from the first thing that we looked at that when the rate of change is increasing, that's concave up. So on which interval or intervals do we see concave up? Only between U and U. So that interval is going to have between 1, but not including 1, just 1, not including 1, because technically here, I have no rate. It's 0. But it's going to be between 1 and 6. And that's the only part on this whole thing that I have concave up. Okay? B, on what interval is the function decreasing at a constant rate? Notice how I said the function is decreasing and not the rate of change is increasing. If my function is decreasing, that means that's happening. So that interval takes place between 6 and 7. So we're going to say the interval 6 and 7. Okay? Find the average rate of change on the interval 2, 5. Now, in the second slide, when we talked about the average rate of change, we wrote out a formula. We're not going to write out a formula here. What we're going to do is we're going to find the interval 2, so that gives us that point right there, and we're going to find the interval 5, which gives us that point right there. Okay, now the average rate of change is the same thing as slope. So the average rate of change is going to be the slope connecting those two dots if I knew how to draw a straight line. Down 1, 2, 3, right 1, 2, 3. The average rate of change is negative because it's a negative slope, 3 over 3, which is the same thing as negative 1. No calculations needed. Also, find an interval where the average rate of change is 0. If the average rate of change is 0, that means you get yourself a horizontal line. So there's several places that I can do that. I could do from here to here. That gives me a horizontal line. Boom. I could do from here to here. That gives me a horizontal line. Boom. Boom. I could do boom. If I really wanted to, I could try to predict what that is, but I'm not going to. So I have a bunch of different options. The option that I'm going to choose is between from this guy to this guy. So between 2 and what is that? 6. Between 2 and 6, I have an average rate of change of 0 because it's flat. Okay? Questions? You're on YouTube. But you can comment. That helps me out. And of course. New problem. Show that the function is quadratic. Oh, my face might get in the way. Let's see. I don't want to move it because it's so nice. We'll see. Let's make sure that my x values are going up by the same number every time. So +1, +1, +1, blah, 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 hooray. So let's test linear. I know it's not linear because I already know it's quadratic. We need to show that it's quadratic. So what do I do? To get from 6 to 0, subtract 6. Subtract 4. Subtract 2. Nothing. That was supposed to be a 0 and it didn't turn out to be. Add 2. Add 4. Add 6. Oh, perfect. Nailed it. Now you can see the pattern forming. However, since this number is not the same throughout, it's not linear. So when we test out its quadraticness, which is a word, we're going to be like, okay, well, let's do it again. Let's add 2. Let's add 2. Let's add 2 again. Add 2 again. Add 2 again. Add 2 again. Add 2, add 2. It is quadratic. And the way you would explain that on like an open-ended problem is you would say that this is quadratic because the rate of change of the function over equal interval consecutive input values is 2. It's the same. Find the average rate of change on the interval -2, 2. All right, now I am going to use that formula. So let me remind you, if I call you A and if I call you B, I'm looking for f of B minus f of A over B minus A. Now, I know what B is and I know what A is. B is 2, so B is 2, and A is -2. All right, so the easy part is looking at the bottom. 2 minus -2 is going to be the bottom. F of B means I do f of 2, which is -4. So f of B is going to be -4. F of B is going to be -4 minus f of A is going to be when I plug in -2, which is 0. So -4 minus 0 is -4. 2 plus -2, double negative makes a positive, is going to be +4. I get -1 as my average rate of change on the interval. So if I were to graph all these dots and connect this point to that point, I'm going to get a slope of -1. Is the function concave up or concave down? It's quadratic. What do I know? The rate of change, remember, this is the rate of change. The rate of change comes from what your linear stuff is doing. The rate of change was -6, -4, -2, 0, positive, positive, bigger positive. My rate of change is increasing, which means concave up. My rate of change went from -6 and got bigger, 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 bigger. Since my rate of change is increasing, it's going to be concave up. Now to do the last problem, find f of 7, I have to use this information over here and keep this going. So I'm going to make you 5, I'm going to make you 6, and I'm going to make you 7. All right, so what we do to get from 0 to 6, what I did is I added 6. According to this guy, every time I add a number here, I have to add 2 more. So in order to get to 5, to find out f of 5, I add 8 more. And then I'm going to add plus 2, 10. And then I'm going to add plus 2, 12. So 6 plus 8 is 14. 14 plus 10 is 24, and 24 plus 12 is 36. F of 7 is, that's a 3, 36. Oh, I like these. I just love them. Just love them. Love them. Can't get enough. Show the table represents a linear function. Got it. Okay, I know what to do. If it's linear, then these numbers go up by the same time. Do these numbers go up by the same number? Yep, plus 1, plus 1, plus 1, plus 1. So this has to be the same thing. Oh, my face. I have to move it. Oh, wait, almost there. All right, so what am I doing? I am adding 3, adding 3, adding 3, and adding 3. This function is linear because the rate of change over consecutive input value equal intervals is 3. What is the average rate of change? Well, the average rate of change comes from the fact that I have a linear pattern of 3 over 1, so my average rate of change is a positive 3. When is the average rate of change increasing? Oh, wait a minute. If my rate of change is increasing, that would imply that I'm dealing with concave up. Well, this is linear, which means it's not concave up. So when is the average rate of change increasing? Never. Never. Sandlot. No, he says forever in Sandlot. Ooh, I'm embarrassed. Very similar to a previous problem that we did just like 2 minutes ago. I now need to find -5, which means I'm going to go back -3, I'm going to go back -4, and I'm going to go back to -5. If going this way was +3, then going this way is going to be -3, and then -3, and then -3 again. So -7 minus 3 is -10. -10 minus 3 is -13. -13 minus 3 is -16. F of -5 is -16. So far, we do these without knowing that we have calculators that can do linear regression and quadratic regression. If those words are new to you, we will do linear regression and quadratic regression at some point. We're just not there yet. We're pretending we don't know. And a lot of these problems would show up on a no calculator section of an AP exam anyway. Moving on. Did it work? It worked. All right. Name the 2 inflection points. Look at this mess. Concave up, concave down, still concave down, concave up. Interesting. Concave up, concave down, still concave down, concave up. And if you're like, well, what about E? What about E? Inflection points occur when there's a change in concavity. Did I change concavity when I went from concave down to concave down? No, 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 no. This was concave up, concave down, concave down, concave up. Name an interval where the rate of change is positive and increasing. Rate of change is positive and increasing implies concave up. So if it's positive and it implies concave up, we're looking for something that looks like this. So where do I see an interval that looks like this? I see 2, actually. 2 intervals that look like that. Here and here. So let's name both of them. Let's name both of them. Let's name between A and B, not including A, not including B, union, and H to forever. So we're going to say H to infinity. Now, technically, I guess this is dangerous because we're assuming that this is just going to keep on increasing forever. But I stole the problem from the internet, so let me make that decision and tell you, yes, friends. Here, let's do that. Happy now? I am. Name an interval with a negative average rate of change. A negative average rate of change implies that it is a negative slope. This is not implying concave down. Decreasing rate of change implies concave down. Negative rate of change or negative average rate of change implies if I were to draw a line from that dot to that dot, am I going to get a straight line going down and to the right? And we have a bunch. Between C and E does that. Between F and G does that, and between F and H does that. So let's name them all. And technically, negative infinity to A does that. So for funsies, let's name them all. Negative infinity to A, union. C to E, union. F to G, union. G to H, union, and F to H. Wow, sir, you must be a teacher. You keep saying union a lot. No, I live in Philadelphia. So go union. Live near Philadelphia, 30 minutes away. What is the average rate of change on interval E, G? Here's E. To get to G, it's just a straight horizontal line. Well, that's 0, boys and girls. Moving on to the next one. A couple more, I think 2 more. Maybe 3 more. On what interval is the function decreasing at a constant rate? The function is decreasing, not the rate of change. So if the function is decreasing at a constant rate, constant implies straight line. That's happening from 2.5 to positive infinity. On what interval is the rate of change positive and decreasing? Rate of change is positive, and decreasing implies it's increasing, and it's also concave down, which gives you the left side of concave down. So the
All right, so I made a little mistake here. I accidentally said that the answer is -1 to 0. It's actually 0 to 1. That's the left side of concave down. Whoopsie daisy.
Name the 2 intervals that have the same positive average rate of change. All right, so let's get rid of the few colors that I added here. Same positive average rates of change. Okay, so you're a negative rate of change, you're a negative rate of change, negative, negative, negative. Well, that makes life a whole lot easier because between here and here, I go up 2 over 2, and between here and here, I also go up 2 over 2. I should say up 2 units over 2 units, because if you really look at this graph, it's actually not up 2 over 2, and that's going to bite us when we do D. All right, so we will say the 2 intervals are going to be between -1 and 0, union, and between 0 and regular 1. Pause it if you have to, because I'm erasing it. Rewind it if you have to, because I erased it. What intervals is the average rate of change -1? All right, so we have a negative average rate of change. So I can't tell. Maybe you're positive, maybe, can't tell. All right, so I have 3 options here. If I were to connect this dot to this dot, that looks like it should be it because you go down 2 units, right 2 units. When you go down 2 units, you go down -2 because each unit on the y-axis moves by 1. But each unit on the x-axis goes by 1/2. So this is actually down 2, right 1/2, 1. Tricky, tricky, tricky. So if the slope looks like 1, it ain't. So that gets rid of u and leaves what must be u. Down 1 over 1, 2 units, which means down 1 over 1, -1 over 1 is -1. And that happens between 1.5 and 2.5. Tricky. Oh, so tricky. Two more. The function, maybe 3 more? Is the function linear or quadratic? All right, well, I've done a bunch of these, so let's just fly through them. Is the function linear or quadratic? Well, let's test its linearity. So -5, -3, no, it's not linear, -1, +1, +3, +5. It ain't linear. +2, +2, +2, +2, +2. At this stage, it's just like, just muscle memory. If the function is quadratic, it is it concave up or concave down? Well, if I want to look at my rate of change, I'm looking at my linear behavior. Shame on me, I should have made sure that these guys go up by the same number they do. If I wanted to check my rate of change, I look at my linear behavior. My rate of change goes from -4 to -3 to -1 to +1 to 3 to 5. Oh, those numbers are going up, which means my rate of change is increasing. So it's concave up. Find the zeros. The zeros are when my graph crosses the x-axis, which means my zeros exist when my y, or f of x, is 0. My f of x is 0 when x is 1, and my f of x is 0 when x is 5. Similarly but opposite, my y-intercept occurs when x is 0. So when is x 0? Only once. When f of x is 5. What is the average rate of change on interval 1, 6? Well, I'm going to use the formula again. F of b minus f of a over b minus a. That is my interval. So I'm going to call a 1, which means f of a is 0. And I'm going to call b 6, which means f of b is 5. F of b is 5 minus f of a is nothing, easy, over b is 6 minus a is 1. 5 over 5, last time I checked. Decaybe Matumbo, not in my house. It is 9:15, and I've been awake for 14 hours. No, 15 hours. 15 and a half. Does the table represent a linear or quadratic relationship? For the first time, these numbers don't go up by the same number. This is not consecutive input value equal intervals, spaces, or whatever. It ain't. Okay? So I can't use the let's do the bunny hops and see if the numbers are the same. Can't do it. This is what I can do, though. Okay? Remember that slope is found by the change in y values over the change in x values. This would be an x value. This would be a y value. Okay? So if I wanted to find the slope between these 2 points, I would do the fact that my change in x value is going to be from 1 to 3, 2, so plus 2, and my change in y value is positive 8. So my slope is going to be the change in y, 8, over the change in x, 2. 8 over 2 is 4. And then I do it again. I do it again because that's not good enough for me to make a determination as to whether or not this is linear or quadratic. If it's the same and it's the same again, it's linear. If it's not, it could be quadratic. Let's pray that it is linear. To get from 3 to 6, I add 3. To get from 9 to 21, I add 14. No, 12. I just got so excited for 21. My change in y over my change in x is 12 over 3. 4 again. Oh, PTL. That stands for praise the Lord. Let's do it again. To get from 6 to 11, I add 5. To get from 21 to 41, I add 20. My y value changes at 20. My x value changes at 5, 4. The rate of change is the same for all 3 possibilities. Therefore, it's linear. Good. I can't imagine you ever being given a problem where this problem is going to be quadratic when you don't have spaces in between. I can't imagine. I do know that it's linear. The rate of change is 4 every time. What is the rate of change? Of the rate of change, Well, that implies that it's quadratic. So it's linear. If it's linear, the rate of change means what's this number right here for quadratic? Well, the number for quadratic is going to be 0, no matter what. Even if I were to write these all out perfectly, it's going to be 0. So what's the rate of change of the rate of change? 0. If I give you a linear function, the rate of change of the rate of change is 0, which means acceleration is 0. In this case, it's meters per second is 0. And yes, I said that correctly. If you're talking about rate of change, you would write that out as meters per second, or meters per second squared. Okay, and that is what we consider acceleration. So this guy's going the same speed the whole time. The same speed, 4 meters per second the whole time. It doesn't speed up, it doesn't slow down. So predict the distance at 14 seconds. Okay, well, at 12 seconds, we're going to add 4 more, so that gives me 45. And at 13 seconds, we're going to add 4 more, so that gets me 49. And at 14 seconds, we're going to add 4 more, so that gives me 53. So the distance at 14 seconds is going to be 53 meters. Kind of a gross problem, and it looks gross. But we have one more to go, and then we're done. Oh, hooray. We finally, hold on. We finally get to use our graphing calculator. And so we're going to do that. Okay, we're going to use our graphing calculator. You get a nice little picture here, but sometimes the pictures aren't good enough. If you remember a lot of quadratics from Algebra 2, you know what's going to happen. You know what zeros are, and you know what factoring is, but we're going to pretend that we don't, and we're going to rely solely on our calculators. So I wonder what this is going to look like on our calculator. All right. We are using a TI-84 plus CE color edition to graph the function that we're given. So, and whenever you want to graph, you're going to hit y equals. Now, the frustrating thing right off the bat is we start out with a negative. Now, the only place on the planet where a negative and a minus sign are different is the Texas Instrument family of calculators. Everywhere else, it's the same, but you know, with Texas Instruments, they decided to make it a little more fun. But let's keep typing x, parentheses, of course. Here's my x right here, x minus 3, close parentheses, x plus 7. Now, what we're going to do first is we're going to get ourselves the graph. Bada bing. Now, this is the graph that you see already included on the slides that I have for you. But, you know, one of the things that we need to find is we need to find exactly where the zeros are. And then at one point, we need to estimate intervals, which requires us to find some more information. So we could find the zeros. We know the zeros by looking at the parentheses. But if we really need to be specific, and if we're allowed to use calculators and we need to find zeros, this is one way to do it. Hit second, trace, and that takes you to calc. Now the second option right there is 0. So we're going to click that. Now I know I have a 0 right there. So when it says left bound, what I need to do is I need to place a little blinking thing that I don't see yet to the left of my 0. Now right now my blinking thing that I don't see is at x equals 0, which is here. So it's going to be way up here where I can't see it. So I'm going to hit left a bunch of times until it goes to the left of my 0. Eventually it'll show up very soon. There you are. So I'm going to go to the left of my 0, hit enter. For the right bound, I'm going to go to the right of my 0. I have to make sure I cross the x-axis, and this is showing me an interval where my 0 lives. For guess, you always hit enter, and I should get a 0 of -7. I do get a 0 of -7, and we can see that. Now we're expecting a 0 of 3, so let's just make sure that that's the case. If I want to find the 0 of this one, you're going to hit second, trace again, that takes you to calc. Hit 2 or go down to 2 for 0, And we're going to do the same thing, but make sure we see our little blinky thing somewhere to the left of our 0. So we can't see it. X is still negative. So once it hits around the 1, 2 area, we should be able to see our blinking cursor, and there it is. Let's make sure it's to the left of where our 0 appears to be. Once you have that, hit enter. Now move to the right. You have to cross the x-axis, otherwise there's no sign change. There's an interval. Hit right again. And our other 0 is 3. Oh, great, we did it right.
All right, for some reason the audio went wacky pants and decided to not work. But we do get zeros. They are 3 and -7. And if you look at our picture, you can see that, yeah, our curve does go through -7 and 3. So those are the zeros. It all makes sense. Now, if you look at the next guy, we're being asked to estimate the interval where the function is decreasing. If you look at what my mouse is doing and not what I am doing, you can see how right there is where the decrease would start, but we can't see the tippy top of the graph. So we're going to use our graphing calculator to figure that out.
Okay, so in order for us to determine where the interval is increasing or decreasing or whatever, we need to find out where that increasing and decreasing changes. So if I go to graph, I see here that it's increasing. Somewhere up here it changes and then it starts decreasing again. Well, I need to know exactly where that change is. So what I can do is I can click zoom and zoom out. Once you do that, select 3, hit enter, and there you have exactly where you need to be. Here's the issue. I can't tell exactly where my maximum is. See, remember, at some point, I'm increasing, and right around here, I stop increasing and start decreasing. So I need to find the x value of right around here. Well, in the last example that you saw, we had to calculate. So I'm going to hit second trace, and it gives me more options. Now, the one that I want is maximum, because where things change is at the maximum peak of my graph. So I can go down to 4 or I can hit 4. And just like I did with the zeros, I need to make sure that my cursor is to the left of my maximum. So my maximum is up here. That's where things change. So my cursor is to the left of the maximum. I hit enter. I go to the right past my maximum and then hit enter again. It shows me an interval where my maximum should be. When it says guess, always hit enter. And it tells me that my maximum is -1.9999999999999. Now, I'm no mathematician, but I'm pretty sure that -1.999999999 is -2. So when I do this problem, I know that all the magic happens at -2, and that's going to be my change in interval.
So the tippy top of the graph ended up being -2. So we now know that our graph, if you can see me draw the picture there, our graph starts decreasing at -2, which gives us an interval of -2. Don't include -2. Goes on forever to infinity. That's where it's decreasing. Now the next guy is asking me to find the average rate of change on a specific interval. What we're going to do is use those graphing calculators again and use the table function to help us out. Away we go.
What is the average rate of change on the interval -3 and 1, you ask? Well, if I hit graph, I can't really see what I have. Now, if you've noticed, you might be thinking, oh, this is the same exact way the graph looked in the problem when you zoomed out. Let's zoom back in. Well, I'm going to go to zoom and I'm going to choose standard because that gives me a regular looking thing. Here's an issue though. If I'm trying to find where action happens in between -3 and 1, I have no clue what's happening at -3 because it's way off screen. I need to find what's going on at -3 when I plug in -3. So here's an option. If I go to second table, I can find out what's going on when x is -3. Right now, I can't see it. But if I scroll up a little bit, I know that when x is -3, f of -3 is going to be 24. I also care about what's going on at f of 1. So at f of 1, I have 16. So f of -3 is 24. F of 1 is 16. I should be able to do my calculations now.
Okay, so by using our graphing calculator, we were able to come up with some nice little values. Now, we didn't need the graphing calculator, it just made it convenient because, we have them, we might as well use them. I'm writing out the formula here, f of b minus f of a. I'm going to label my interval a and b, and I'm using the table that we had to plug in points and get ourselves a few numbers. So that's it. And what the average rate of change does, and I don't know if I'm going to show this on the video, I don't remember, but what it does is it gives us a straight line distance from the point determined by -3 to 1. And that's exactly what average rate of change is. It's the average. So straight line, ignore the curves. Ignore the curves. So it's usually around this time of the video where I say something cute. I try to beg you for more subscribers and asks for likes and try to grow my YouTube and make me sound popular. This is also where I tell you how much I love you and you're the best. And then I do something like say bye a bunch of times, but what am I doing? I don't know. But I'm just going to say bye now, and I'll hold that bye until the video cuts out. Bye. What could I possibly be talking about? I'm now drawing a graph. Bye. Seriously? Why isn't this over yet? Bye. Oh, that's me drawing the straight line distance like I told you about earlier. Bye. All right, hurry up, you idiot. Bye. I'm running out of air. Bye. I give up.
What up, what up? Welcome to part 2, the second review of AP Precalculus. Today we're going to talk about Unit 1, Sections 1.4, 1.5, and 1.6. We're going to talk about limits. We're going to talk about local extrema. We're going to talk about cubic functions. I'm extremely excited. Let's first talk about what graphs of polynomial functions look like, okay? This section kind of broadens things a little bit. We talk about more topics, and it's important for us to know, generally speaking, what graphs of these guys look like. All right, so let's start out with the old cubic, okay? A cubic function is going to look like this. Notice the two bumps. Now, if I were to throw a negative in front of that cubic, you are going to take this guy and flip it upward, which means it starts up here and goes bump, bump, and ends down there. That is a cubic. When you turn the degrees up, numerically speaking, we get a quartic, and that looks like more of a W. So 1 bump, 2 bump, 3 bump, and then you make your way back up. Notice how you started going up and you end going up. It's the same thing when you have a quartic. All right, if we throw a negative in front of it, the same behaviors occur. You start at the bottom, bump, 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 end at the bottom. Like Drake, but he started from the bottom, and you know where he is now? He's up here. Yeah, good old Drake. And then the process just continues, x to the 5th. Start down here, 1 bump, 2 bump, 3 bump, 4 bump, end up here. Throw a negative in front of it. Okay. Start up here, bump, 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 bump. So as you can see, when we deal with odd highest degrees, okay, odd degree, if it's a positive odd degree, so the same thing would happen with x to the 7th, regular x, x to the 9th. If it's a positive odd degree, it starts from the bottom left and ends on the top right. Starts at negative infinity, ends at positive infinity. If it's an even degree, so x to the sixth, x to the fourth, parabola, x squared. If it's positive, it starts up top, ends up top. When you throw negatives in front of these guys, you spin things upside down, and that's the main difference between the two, okay? So very basic ideas of what the graph of a polynomial function could possibly look like when the degrees are different. Now, we're going to talk about local and absolute maxima. Now, what if I took just a sample cubic, right? Looks something like this. A local maxima is if I know things are going to end up in infinity all the way to the left and all the way to the right. That's great. But I kind of care where I hit the top of my mountain and the bottom of my valley. What are those? What are those? Remember that? The top of a bump is called a local maximum. The bottom of a bump is called a local minimum. Now you might be thinking, all right, well, then what's the absolute maximum and the absolute minimum? In this case, I don't know, because it keeps on going forever upward and it keeps on going forever downward. So the absolute maximum is just going to keep going more and more and more and more and more. Same thing with the minimum. However, if I were to give you a problem and just decide, you know what, I'm going to put endpoints right here. And I'm going to go like this. Okay? And if I were to ask you what's the absolute maximum and what's the absolute minimum, the absolute maximum is going to live at the highest part of the graph, whether it's the endpoint or not. So absolute maximum is going to live right there. In this case, given the picture that I drew, you would appear to be my absolute minimum. Okay. So a lot of questions are going to be asked, like, what if I give you an x cubed plus something x squared minus whatever? It's going to ask you maybe where local maximums and local minimums exist. Okay, now we will see problems like that, and we will be able to use the concept of zeros to figure that stuff out, which is what we're seeing next. Factoring. Let's just say I give you something like this. X squared minus x minus 6, and I ask you to factor that. Okay, simple. You come up with two numbers whose sum is negative invisible 1 and whose times or product is negative 6, and you would get x minus 3, x plus 2, nothing to lose sleep over. However, if I were to turn u into equals f of x, or better yet, pretend that f of x is 0, now I'm asking you to find zeros. This requires the zero product property. When you have the zero product property, you take each parentheses and set them equal to 0. Take each parentheses and set them equal to 0. Now, when you have just a number and just an x value, you're just thinking opposites. You add 3 to both sides, one of your zeros is 3. You subtract 2 from both sides, one of your zeros is negative 2, nothing to it. If I were to throw like a 5 in front of here, then I would add 3 divided by 5 and I'd have a fraction, not the end of the world. That's not what I'm really focusing on here. We need to know how to factor. Hopefully in AP Precalculus, you already know how to factor. But what if I give you something that's a little bit more crazy than a quadratic? Like, what if I ask you to find the zeros of this guy? X to the 4th minus 16x squared equals 0. Okay? At this stage in AP Precalculus, they really don't care much about factor by grouping. And if I'm wrong, I apologize. But you're not going to see factor by grouping a whole lot. One of the main methods that you're going to see while factoring is there something in common, a greatest common factor that we can pull out? And in this case, we could bring out x squared. What's left over? X squared minus 16. Now, am I able to look at this and find my zeros? Not really. Okay, not really. Now, I have x squared, nothing I can do there. Can I do anything with x squared minus 16? Ooh, that's a difference of squares. So I can turn that into x plus 4, x minus 4. And now when that's equal to 0, I can just say, all right, let's do the easy ones first. One of my zeros is negative 4. One of my zeros is positive 4. But x squared equals 0 implies that 0 is being seen twice. This is called multiplicity. If one of your factors has an exponent, then that 0 has a multiplicity of whatever exponent that is. So this is a multiplicity of 3. All right. Now, knowing what I know, if I wanted to draw a very rough sketch of this, and it's possible that I might be jumping the gun here, and I'll do this again in a later example. But if I wanted to sketch this, right, draw this out without using a calculator, I know that my graph is going to go through negative 4. It's going to hit 0. And when I say hit 0, I mean hit 0 and not go through. You'll see why in a second. And it's also going to go through regular 4. I know this is a quartic where the leading coefficient is positive, so I expect it to look like a W, right? Now, magic happens whenever you have a multiplicity of an even number. And stupid me, I put multiplicity of 3. It's actually multiplicity of 2. I have no clue why I put 3 there. But when you have an even multiplicity, which I do, when you graph things, when you have a normal 0, it just goes through that number right there. But when you have a multiplicity of an even number, it skips off the x-axis. So that would be a rough sketch of what x to the 4th minus 16x squared looks like based off of the fact that we have multiplicity of 2. If it was a multiplicity of 4, a multiplicity of 6, similar behaviors would happen. What about a multiplicity that is odd? You still go through. Okay? Now, what if, you might be thinking, we have a graph, right, that looks something like this. Okay, I draw a picture. That is an awful coordinate plane. But I draw a picture, and it's a cubic, but I only have one spot where my line is going through my x-axis. I know it's a cubic. I know it's a cubic, but it's asking me how many real zeros I have and how many complex zeros I have. Okay, well, a real 0 is going to be wherever it crosses your x-axis. I have a real 0. Now, the amount of total zeros that I have comes from the degree on the leading coefficient. I'm going to have 3 total zeros. Since one of them is real, that means 2 of them are not. So we would say 2 of them are complex. Now, complex means it has an I. A complex 0 is in the form A plus BI. This is just a shot in the dark. I have no clue if this is accurate or not. But if I were to tell you that one of the zeros that's complex is negative 3 plus 4i, and I said, okay, great, that's one of them. Find the other. And if you're like, oh, I don't know, it's simple. If you have 2 complex zeros and you know one of them, the other it's going to be is conjugate. The conjugate is when you flip the sign in front of the I term. So the conjugate is going to be negative 3 minus 4i. So if I give you something like x to the 6th power, I know x to the 6th power is going to have all these bumps, but I also know that I'm going to have 6 total zeros. What are my possibilities? I could have 6 real zeros. I could have 4 real zeros and 2 complex. I could have 2 real zeros and 4 complex, or I could have all 6 complex. Okay. Now, again, what would this look like? 6 complex look like on a coordinate plane? Well, I have a coordinate plane and I have bump, 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 where nothing crosses the x-axis. And if I were to tell you that one of these zeros is 5 minus I, you would say, all right, the other one is going to be, flip that sign, 5 plus I, conjugate. Okay? Complex numbers. All right. On the theme of graphing, again, much wider topic with these three sections. We're dealing with more than one thing. An even function is something that when it's graphed looks a little something like this. Speaking of like w to the fourth power, which we saw just a little bit ago. An even function would look something like this. Now, graphically, and I'll give myself some credit, that's a pretty good looking picture. Graphically, what an even function looks like is if I were to take the left side of my graph, and if I were to take my y-axis and my right side of the graph and fold it over, do I have the same exact thing? In other words, is there a reflection over the y-axis? If there is a reflection over the y-axis, it's an even function. So something like x to the fourth minus 16x squared, which is what we saw a couple minutes ago, was an even function because that picture looked something like this. Okay. Let's bring that up. Now, how can we test this? How can we make sure? What if I don't give you a picture and I tell you, is this even or is this odd? Well, I'll tell you what we do. One thing that you do is if it's an even function, there is a rule that says if I were to replace an f of x with f of negative x, it's going to end up being still f of x. What that means is if I plug in something like 3, right? And when I plug it in, I get something like 10. If I plug in the opposite of that, negative 3, I'm also going to get 10. Now, the way I show that here is if I were to replace every x with negative x, do the math, do I get the original function that I started out with? So if I replace x with negative x, so negative x to the fourth minus 16 negative x squared, well, negative x in parentheses to the fourth is just x to the fourth, minus 16, and negative x squared is just positive x squared. It is the same thing. That's what makes this even. The other way that you can make this even is look at every single term. Look at every single variable. Does it have an even exponent? It does. Well, then it's an even function. Simple. Even if I were to add like over here, and I'll erase this in a second, even if I were to add 5, and if you're thinking, well, hold on, time out, you just added a brand new thing, and I don't see an even exponent attached to a variable. Yeah, you do. There it is. That is an even function. Okay? All right, let's get rid of that. If there's an even, there's an odd, so let's find our odd. An odd function looks a little bit different, looks a little bit worse. All right, so let's graph a full coordinate plane. I am nervous about drawing this picture, but let's see what happens. All right. Oh, see how I was nervous? I had every right to be. It's not good, but it's not pretty either. Basically, what an odd function looks like is if I were to take this picture and spin it 180 degrees, do I get the same picture? If the answer is yes, yes. If I were to take this guy and spin it 180 degrees, I do get the same picture. Did I make a really nice looking picture? No, and I was nervous that that was going to happen, but, you know, it happened. So if I give you something that is like x to the fifth, plus 3x to the third minus x, and I'm going to ask you, is that odd? There's two ways that we can test this out. One way that we can test this out is if I were to replace every x with negative x again, am I going to be able to rip out a negative of everything and have f of x left over? In other words, if I plug in negative x, will my solution be the opposite for everything of what I started out with? Will I get negative x to the fifth minus 3x to the third plus x? Well, let's find out for this guy. Let's replace every x with negative x. So negative x to the fifth plus 3 negative x to the third minus negative x. Negative x times itself 5 times is still negative x to the fifth. Negative x times itself 3 times is going to be negative x to the third. Multiplied to 3 is negative 3x to the third. A double negative is a positive. Is this the complete opposite of that? Positive became negative, positive became negative, negative became positive. That's odd. So what's an even look like? Well, I'm sorry, what's a neither look like? Yeah, just, something like that. Or if I were to graph that, there's no folding it over and there's no spinning it upside down. Now let's talk about an old familiar friend, end behavior and the limits. End behavior is basically, if I were to give you a picture that looks like this, right? I'm just going to draw it out. And I asked you about end behavior. What I'm doing is I'm saying, what's going on as x moves to the left? Or what's going on as x moves to the right? What we use to figure this stuff out is extremely important. You see it in calculus all the time, and it's called limit notation. This is the x-axis. We write out what's going on as x goes to the left as limit as x approaches negative infinity. That means as x goes to the left, where is my function going? So if this function was called f of x, in this particular case, my limit of f of x, or my limit as x approaches negative infinity of f of x means where is that purple arrow going up here as I move more to the left? Well, it's going to go up more and up more and up more, which means it approaches a positive infinity. As I go to the left, my arrow goes up, which makes it positive infinity. Similarly, but opposite, my limit as x approaches positive infinity is asking, what's happening to my arrow here as I move to the right? Well, as I move to the right, this arrow is going down. So the limit as x approaches positive infinity of f of x is negative infinity because that arrow is going down. Or as Fallout Boy would say, it's going down, down. Remember them? They were really cool about 20 years ago. Have I hit all the topics that I need to hit? Yes! Let's move my face. Let's move my face. All right, let's just push this down. So strong. So strong. All right, let's do, I think, 6 problems. No calculator whatsoever, so you're not going to see me awkwardly stare into a void if you watched my last video. If the function is f of x, so we have a cubic. If the function is f of x equals x to the a and x plus 3 to the b, find a and b. All right, so this implies that I have a 0 of 0 and a 0 of negative 3. My line goes through negative 3. Which means this has a multiplicity of 1, which means my exponent is 1, which means b is 1. However, we skibbity bop bop no yes yes right off of this. I'm sorry, we skip right off of 0 there. Boom. Which implies that we have an even exponent. Forgot the word. So if this is a cubic, which it is, and it's an even exponent, a has to be 2, which means this function is x squared because x ricochets off, and x plus 3 to the first because it goes through -3 once and only once. Right off the bat with multiplicity. Find the limit as x approaches infinity. As x moves to the right, what is my graph doing? It's moving upward. So my limit as x approaches infinity is infinity. Infinity Wars! Find the local maxima for all x values. The local maxima, or local maximum, is probably what I should have said. The local maxima or maximum for all x values is going to be just this guy right here. Since you go on forever and you go on forever, my local maxima is going to be -2, +4. So my local maximum is the point at the top of this mountain, -2, +4. And again, if you're like, but this line keeps on going on forever. Exactly, which makes it not local. Okay? Find the absolute maximum or maxima. Again, we're implying that maybe there's more than one. There's never more than one for absolute unless it's a tie. Something you'll learn in calculus. Find the absolute maxima on interval -1, 1. So let's find interval -1, 1. There you are. Interval -1, 1. So in this case, my local maximum is, I go to 2, then I go to 0, then I go all the way up for 4. My local maximum is an endpoint. And that endpoint, my absolute maximum is an endpoint, and that endpoint is 1, 4. If you're dying to know, well, what's the local minimum or what's the absolute minimum? In this case, looking at this interval, the local minimum and the absolute minimum are both the same, and it's 0, 0. What's the inflection point? Oh, did we talk about inflection points? Not in this section, but we're hearkening back to an old friend. An inflection point is where concavity changes. I have a picture that looks like this. Where do I go from concave down to concave up? Right around here, which is right there exactly on the blue scratchy thing, which is the point -1, +2. Gang. Questions? Oh, man. It's done. What degree is this polynomial? Okay, well, it's even because they both end going up. We have 1 bump, 2 bumps, 3 bumps. So you tell what the degree is by saying my degree is the number of bumps that I can see plus 1. So the degree of this polynomial is 1 bump, 2 bumps, 3 bumps, 4 bumps, or 4 because it's 3 bumps plus 1. Is this function even, odd, or neither? Well, can I take this guy and fold it over and get the same exact thing? No. Can I take this guy and spin it upside down and see the exact thing? No. So it's a neither. How many zeros are real and how many are complex? Well, first off, my degree is 4, which means I'm going to have 4 total zeros. How many times does this picture cross the x-axis? No times. No times at all, which means there's no real zeros, which means there would have to be 4 complex numbers that are zeros. If 3 minus 5i is a complex 0, what is another complex 0? Take the number, or take the sign rather, in front of the I term and flip it. 3 plus 5i, that is called the conjugate. Last but not least, find the limit as x approaches -infinity. Where is that arrow going as I move to the left? Well, it's going way up, way up, way up, and it's going up super fast. So my limit as x approaches -infinity is +infinity. Fun. Ooh. Find the leading term. Okay. The way you can find the leading term of something that is factored, and that's what this is factored. The way you find the leading term is you multiply the highest degree terms in every parentheses together. And then if there's a sign or another term floating out here, you multiply that as well. We have one added part, which is divide by 2, so I have to kind of include that as well. Negative x times x is negative x squared times 2x is negative 2x cubed, which simplifies to negative x cubed. My leading term is negative x to the third, which is going to tell me that the behavior of this cubic is going to go like this. So a normal cubic starts from the bottom like Drake and works its way up. This is flipped upside down, okay? Let's clean this mess up because now I have to find the zeros. The way you find the zeros is you take each factor that contains an x and you set it equal to 0. Well, you're going to be easy because you're just going to be 3. You're going to be negative 2. You not so much, so I'll set you up 2x plus 5 equals 0. Subtract 5 from both sides, and you now have 2x equals negative 5. Divide both sides by 2, and your last 0 is going to be x equals negative 5 over 2. So my zeros are going to be 3 because it's the opposite, negative 2 because it's the opposite, and negative 5 over 2. Remember a couple minutes ago where I said that my picture has to look like this? It's asking what my picture is going to look like as x moves to the right. My arrow, as I'm moving to the right, is also going downward, which means the limit as x approaches infinity is going to be negative infinity because my arrow is going down and to the right. I love these problems. This requires me to make what's called a sign graph. You will see this a ton of times in calculus. I know we're not there yet, but this is how you make a sign graph. Take all your zeros and put them on a number line. Put them in order. So I had negative 5 over 2 is negative 2.5, so that's going to be barely to the left of negative 2. And I also have 3, which is way over here. No multiplicity to worry about, so I don't have to worry about things skipping. If I were to graph this, I know I get something like that. Nothing's going to skip on the x-axis. So when I graph this, I know that as I draw this picture out, it's going to go through the zeros once for all 3 of them. So I have to start from the top left. Okay, it's going to go through there, come back up, hit 2, come back down and go through 3. That's what my graph is going to look like, give or take. Why is this useful? This is f of x, or at least a sketch of f of x. I care about when f of x is positive. Where's f of x positive? Here, because it's above the x-axis, and here, because it's above the x-axis. How do I demonstrate these two intervals? This interval is everything to the left of negative 5 over 2. So from negative infinity to 5 over 2, not including 5 over 2. And if you're wondering, why don't you include 5 over 2? Because at 5 over 2, it's neither positive or negative, because at negative 5 over 2, it's 0. So that's my one interval union. My other interval is going to be between negative 2 and 3. Sign graph. In between which two zeros does a local maximum occur? Well, according to my sign graph, it's going to look like this. So you're going up forever, so no local maximum there. You're a local minimum, so you're a local maximum. And my local maximum is going to occur at negative 2, 3, that interval right there. F of x equals 3x cubed minus x squared minus 6x. Find the zeros. Ooh, we have to factor and set it equal to 0. So let's set it equal to 0. And I see an x is in common. Let's rip it out. That leaves us with x squared minus x minus 6. Can I factor that any further? Sure can. 0 is going to equal x times x. Let me think. Two numbers that add up to -1 and multiply out to -6. -3 and +2. So I have three factors that contain x. U, so set that equal to 0. X is equal to 0. X minus 3 is equal to 0 just means I have another one that is 3 because there's no number attached. Don't overthink it. And since there's no number attached, it's the opposite of U, so it's -2. So my three zeros in this case is x equals 0, 3, and -2 in no particular order. Now, this is asking me to find the limit as x approaches -infinity. That is a cubic where the leading coefficient is positive. Okay, so it's going to look like this. So when it's asking me, where is my arrow going as x moves to the left? My arrow is going downward, which means as x approaches -infinity, my graph is also going down, approaching -infinity. Now, I'm asking you, where is f of x negative? That requires us to make a sign graph just like I did for the last time. So I'm going to make a sign graph. I'm going to put my zeros on it in order. So -2, 0, 3. My graph is a Drake cubic, which starts at the bottom, goes up through -2, peaks out, goes down through 0, bottoms out, and goes up through 3. So starts from the bottom left, goes up through -2, peaks out, goes through 0, bottoms out, goes through 3. I now care about where f of x is negative. Where does that happen? Well, whenever it's below my x-axis. So it's negative here, and it's negative here. So where is f of x negative? From -infinity to -2. So -infinity to -2, union, and between 0 and 3. Again, don't include those because those are 0, which is neither positive nor negative. Now I need to sketch f of x. Now, a sketch is an accurate picture. It's not exact by any means, but I'm going to try to be as exact as I can, knowing that I have decent numbers to deal with. So I have to be out to like there, so I'm going out to 4, 1, 2, 3, 4. Okay. My zeros are at -2, 0, and +3. I am purposely not labeling my y-axis because I'm not going to worry right now as to how high it goes up and how low it bottoms out. That's something that calculus will help me out with. I start from the bottom. I go up through -2, go down. Let's widen this out and go up. Okay, so obviously as the intervals are spread out a little bit more, you can expect your bowls or your hills to be bigger. Is this exact? No. Is this accurate? Yes. Okay. Ooh, an old friend. Find the degree of a function. We know from section 3 that if I wanted to find out if something is linear, I need to add these guys up. And if I want to find if it's quadratic, I need to make sure that these guys aren't the same and maybe these guys are. Well, first thing I need to check first is, do these guys go up by the same number? They do. Hooray. When those numbers happen, you know, if you watched my last video on sections 1-1 to 1-3, I struggled with this phrase. And I think I remember that the phrase is consecutive input value equal length intervals? Or is it consecutive equal length input value intervals? I don't know. There was always a word in the last video that I kept forgetting to say, and I think I got it this time, but I clearly did. These go up by 1. Yay. Let's check if it's linear. It's not. But let's check if it's linear. Add 7. Add 19. Is it add 19? It is add 19. Let me see. That is a 9. I want to make sure that that's a 9. Add 37. Add add 61. Checking my work, checking my work, checking my work, and I think I am okay. Probably should do these ahead of time, but nah. All right, what do I do? Add 12. Add 18, so it's not quadratic. Add 24. All right, not quadratic. Is a cubic. Add 6. Add 6. It's a cubic. So find the degree of the function. It's third degree, like the burns I have. That's not true. I don't have any third degree burns. Is the function even, odd, or neither? All right. I don't think it's even because the degree is 3. So it's definitely not even. Okay. If the degree is 3, it could be odd, but it still could be neither. So the test for something being odd is if I were to make u negative, right, and plug u in, do I get the opposite output, right? So if I take -1, right, and it looks like what we're doing every single time is we're basically taking our number and multiplying to itself 3 times. So if I take -1 and multiply it to itself, do I get -1? Yeah. If I take -2 and multiply it to itself, do I get -8? Yeah. If I take -3 and multiply it to itself 3 times, do I get -27? Yeah. 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 So is it even? No. Odd? Yep. Neither? No. For x is greater than 1, is the function concave up or concave down or neither? Again, we're going back to the first 3 sections of Unit 1. If something is concave up, it looks like this. That means the rate of change is increasing. Okay, remember that phrase? You need to. Hopefully you do. If something is concave down, it looks like this. That means the rate of change is decreasing. Rate of change is found by going to where it's linear and seeing what your numbers are doing. 7 turned into 19, got bigger, which turned into 37, got bigger, which turned into 61, got bigger. Oh, look, my rate of change increased. So what is it? Concave up. Again, something from back in the day, find the average rate of change on the interval 2, 4. The formula for average rate of change is f of b minus f of a over b minus a. Well, what's b? What's a? Well, a and b come from your interval, 2 and 4. So let's clean this mess up. A is 2, b is 4. So a is 2, b is 4, f of a is 8, f of b is 64, like my favorite video game system from when I was a kid. F of b is 64 minus f of a, it's minus 8, over b, which is 4, minus a, which is 2. 64 minus 8 is 56. 56 over 2 is 28. My age in a couple years. Let's do one more. Oh, thank you, Jesus. It is one more. Find the zeros. Oh, okay. Find the zeros if I'm given a regular old polynomial is found by setting it equal to 0 and factoring. Can I rip anything out from both of them? Sure can. X squared. That leaves me with x squared minus 9. Ooh, a difference of squares. 0 equals x squared. I can factor that by thinking of 2 numbers that add up to 0 but multiply out to -9, x plus 3, x minus 3. So my zeros are going to be x squared equals 0, multiplicity 2, -3, and positive 3. So my zeros are x equals 0, -3, positive 3. Is the function even, odd, or neither? Now, if it's odd, all of these would be odd. It ain't. If it was even, all of these would be even. They are. So it's not neither. Now let me double check. If I replace this with negative x, do I get the same thing? Negative x to the fourth is still x to the fourth. Great. If I replace this with negative x, do I still get the same thing? Negative x in parentheses squared is still x squared, so nothing changed. Hooray, this is even. Yippee-yi-yo. Where is f of x negative? I need to make another sign graph. I have a bunch of zeros at -3, 0, and +3. What type of function do I have? I have a degree 4 where the leading coefficient is positive, so it's going to make a W. All right, so when I graph this, I have to be very careful and remember that I have a multiplicity of 2 at 0. So wherever I'm supposed to go through 0, I won't, and I'll ricochet and I'll come back around to when I hit 3. So I'm starting from the top, the opposite of what Drake did, goes through 3. I approach 0, ricochet off because the multiplicity is 0, come back up through 3. So it's negative underneath the x-axis here and here. Now you might be thinking, why don't you just draw a blue line across everything? Because it's not negative at 0. When it comes up and ricochets, it still hits the x-axis, which means at 0, it's 0, which is not negative. Gotcha. So I'm going to say that my intervals are between -3 and 0, not including union, and 0, 3. So when I sketch this graph, I'm going to purposely not label the y-axis. 1, 2, 3, 4. 1, 2, 3, 4. I'm going to make sure that my line goes through -3, comes back up, bounces off of 0, comes back up, and goes through regular 3. Okay, so, oh golly, I started out weak. Here I'm trying to end this thing, and I can't even draw lines, curves, whatever. I'm making it green, my favorite color. Bounce. Yeah. See how the left side and the right side are just mirror images of each other? Because it's even. Even, Stephen. That was a lot of fun. Now, AP Precalculus is probably going to have you take a test on sections 1.1 through 1.6. So watch this. Watch my last video of 1.1 through 1.3, and that should adequately prepare you for whatever AP exam that you should expect. This covers pretty much everything. I may have missed a thing or two, but this covers the nitty-gritty where you should be able to get an A on a test if you understand everything we did here. Okay? Thank you guys for watching. I appreciate you. Love you. Bye. What up, what up? Today in AP Precalculus land, we're going through 4 sections. They all talk about rational equations. Rational. That means fractions. So let's get right to it. First thing that we're going to talk about is zeros, asymptotes, and end behavior. When you graph rational functions, you're expecting weird things to happen, okay? Things that look something like this, and you're like, what the heck is all of that? And it looks sad, because it is sad. So you're expecting strange things to occur, things crossing the x-axis, things non-existing. That's where all of this info comes into play. First things first, let's talk about zeros. Now, a zero is found whenever you take your f of x or your y, and every single thing that we look at is going to be from the point of view that the denominator is q of x and the numerator is p of x. So if I'm finding the zeros, you're pretending the y is 0. And the way you find the zeros is you set the denominator, who cares, and set the numerator equal to 0. And if you're like, well, wait, what do you mean who cares about the denominator? Look, baby. If that was 0 and you multiply both sides by q of x, what's going to happen to q of x? That's going to happen to q of x. You are gone. We don't care. So chances are the numerator is going to look like a polynomial, or maybe it already looks something like this, and you can do zero product property on it. So that's how you find the zeros. You look at the numerator, factor it if you must, and see if you could do zero product property to find out where your zeros exist. so that's zeros. What are asymptotes? Asymptotes is going to be wherever your graph explodes. Now, the only thing that makes an equation that's also a fraction explode is whenever the denominator is undefined. Undefined means, is there a number that you can plug into the denominator that gives you 0? So asymptotes exist at these moments where the denominator is equal to 0. Now, asymptotes, again, and if I were to draw like a similar picture that I drew before, I don't know why I'm dashing these, asymptotes live at a vertical line where the explosion takes place. Now, since this vertical line is a vertical line, the equation of a vertical line is going to be x equals some number. So if I gave you something like x minus 3, blah, 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 equals 0, then you would do the opposite and say that number is 3. That is where an asymptote exists. Now, what also could possibly exist is a horizontal asymptote, which means a line that goes through there where my graph will neither touch it horizontally. That's where end behavior takes place. So the end behavior takes place when we're talking about my limit. So what's my equation doing when x is approaching infinity or negative infinity? Okay, now there's 3 different cases that we're going to look at, and in all of those cases, they're all going to be different. Okay, so I'm not going to just come up with some blanket example. All I know is when my limit is approaching infinity, that means this blue line is going to approach this red line but never officially touch it. Same thing on the left. So me trying to say it's always going to be this, we don't know. That's part of the fun. So let's look at possibility number 1. What if I give you an equation where the numerator and the denominator have the same exact degree? What if the numerator and the denominator has the same exact degree? I'm going to put up some, pictures of cases like this, starting with, a regular x something over x something, and then move my way up. And as you can see, explosions take place. You can see my end behavior doing something to the left, my end behavior doing something to the right. Lots of stuff going on. But like the main idea of a graph is going to look something like this. Or maybe it looks something like weird like this. But what's going to happen is the left and the right are going to approach the same area. And in certain cases, we might have things going in. I'm jumping the gun. I'm saying too much. What matters is the asymptotes. I thought I misspelled that. I spelled that right. It's a terrible word. The asymptotes. Again, the asymptotes exist whenever the denominator is undefined. So if I give you just a regular guy like x minus 4 over x minus 3, okay, and if that's wrapped in parentheses and you have a bunch of parentheses over here and a bunch of parentheses over here, as long as you have the degree on the top being the same as the degree on the bottom, even if that's not the case, the vertical asymptotes are going to be whatever makes the bottom 0. So in a case like this, x equals 3 is going to be a vertical asymptote. Okay? Now, I thought a simp was somebody who was trying to get on my Instagram and get my attention. I'm just joking. That doesn't happen. End behavior. Now, this is where we're talking about limit stuff. Okay, so let me give you just a very, very, very basic example of something where the degree on the top is the same as the degree on the bottom. And let's just say x is approaching regular old infinity. So if I said x squared plus x minus 6 over x squared plus 5x minus 9, and you're like, I can't factor the bottom. How am I going to find the end behavior? Simple, don't worry about it. This is what you do. Whenever you're being asked to find the limit of a polynomial over a polynomial, take the leading term in the numerator, take the leading term in the denominator, and forget everything else. So our main focus is going to be x squared over x squared. And you might be thinking, well, that simplifies nicely to 1. And that is true. And so let's take the limit as x approaches infinity of 1. Usually if you're being asked to find the limit as x approaches anything, you just plug in that number for x. There's no x to plug in. So my answer is just 1. And if you're thinking that's just a bit too easy, give me another. Fine. Limit as x approaches negative infinity, so let's flip it around, of 3x squared blah 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 over regular x squared blah blah blah. We don't care about the blah blah blah. So what happens is this simplifies, and the limit as x approaches anything of 3 is going to be 3. So to find the limit, whether it's positive or negative, the limit, whether it's positive or negative, is found by doing the leading term divided by the leading term. When the degrees are the same, they cancel each other out, and whatever number is left over is your answer. Now, what I just said, as far as the way you find the limit of a polynomial over a polynomial, you just take the leading term. That's the case for all of them. It's the case for every single one. But in the case where the degrees are the same, it's always going to be a constant number, a number found by doing the leading coefficient divided by the leading coefficient. So that's when the degrees are the same. What if the degree in the numerator is bigger than the degree in the denominator? Okay, so something like x cubed over x. What does it look like then? Well, I'm going to throw some pictures up on the board, and as you can see, not on the board, on the screen, and as you can see, things kind of get a little curvy. Okay, curvy's dreamland. And some of the problems that we get, and I think the first picture that I showed you looked something like this, where it kind of looks like a sideways hyperbola thing, and you're like, what is that? What is that? And if you're wondering, all right, well, maybe I can squeeze in a vertical asymptote there, but I certainly can't squeeze in a horizontal asymptote. I'll show you what I mean. Vertical asymptotes are exactly the same. Vertical asymptotes are going to behave exactly the same. You have x plus 3 on the bottom as a factor somewhere. All right, x equals negative 3 is going to be a vertical asymptote. Nothing to think about, bada bing. Now, what occurs here is we are going to have what's called a slant asymptote. A slant asymptote. Okay? So if I give you a problem just like this, and I'm asking you to find what is, like, let me give you this exact example. X squared minus x minus 6 over x plus 4. And I asked you to find the slant asymptote. The way you find the equation to a slant asymptote is you do polynomial long division. Yeah, I said it. You could do synthetic division, but I prefer polynomial long division, so let's set it up. X plus 4, x squared minus x minus 6. Your answer, ignoring the remainder, is going to be your equation for the slant asymptote. One more time. Your answer, ignoring the remainder, is going to be your equation for a slant asymptote. So let's do some long division. X times what is x squared? X times x is x squared. Put an x up there. Now we take that x, we multiply it by the dividend, and we do x times x is x squared. X plus 4x, or times positive 4, is plus 4x. And then we subtract the entire row here. Okay, so you are now negative. X squared cancels out. Negative x minus 4x is negative 5x. Drop down the negative 6. Funzo. X times what is negative 5x? Minus 5, of course. Take that negative 5, multiply it to this guy, so negative 5x, negative 20. Subtract the entire thing, which means flip the signs. You go away. We have a remainder of who friggin' cares. The equation of my slant asymptote is x minus 5. All right, I had to do a location change because my kids started barging into the dining room. Children, can't live with them. There's probably an end to that sentence there. End behavior, speaking of end behavior is what happens as my limit seems to approach something. Well, it all completely depends on what you have as far as the equation, but don't let it bother you too much. What we see with pictures like this, okay, with graphs like this, is this picture should keep going like that way, and this picture should keep going down that way. Okay, so what we can expect is a similar thing. So if I give you like the limit as x approaches regular infinity, here, let me quick do this. Let me maximize my screen again. As limit approaches, or x approaches infinity, of something like negative x to 4x to the fourth over x squared. All right. Well, clearly the numerator is greater than the denominator as far as degrees go. You're going to, again, and by the way, plus stuff, minus stuff, blah, 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 blah. Let's pretend that you're the leading term and you're the leading term. When you're the leading term, simplify as much as you can. Expect the numerator to dominate the denominator, and you get negative 4x squared. Now, if I were to take this and plug in infinity to negative 4x squared, what's going to happen is I get negative 4 times infinity squared. Infinity times infinity is infinity, and multiplying that to a negative number is going to become negative infinity. So very similarly to the last slide, what we do is we take the leading terms, simplify it, expect the x to be larger in the denominator and the numerator, and then plug in infinity, and you're either going to get positive infinity or negative infinity. It's always going to be the case that way. And if I gave you something like, let's find the limit as x approaches negative infinity of, let's just say, x to the fifth over x. You simplify that, you get x to the fourth, you plug in negative infinity to the fourth, and negative infinity times negative infinity times negative infinity times negative infinity is positive infinity. So you're going to get one of the infinities whenever your numerator is greater than the denominator. So last but not least, what if the denominator is greater than the numerator? Okay, let me show you a bunch of graphs again. We see a lot of similar behaviors. These are probably more like when they're equal and less like, we're not expecting any slant asymptotes. We're still going to have vertical asymptotes, and the vertical asymptote stuff is still going to exist whenever you have something on the bottom. So, even if I have nothing at top, a 1 at top, you still have, like a vertical asymptote living at 3 in a case like this. Now, my end behavior, if my denominator is bigger, let's say I had the limit as x approaches infinity of 3x to the fifth over x to the ninth. Okay, you simplify that as much as you can, so 3 over x to the fourth. Now, let's make sense of what's about to happen. My x is greater than, in the denominator, than the numerator. As x gets larger, like let's just pretend like we're testing this out for the first time ever. Let's plug in 1. I get 3. Let's make x bigger. Let's plug in 2. Okay, 2 times 2 times 2 times 2 is 16. That 3 just became point something, like something that's near 0. If we were to plug in 5, okay, I now have 3 over 625. That number, 3 over 625, is almost 0. If I plug in 10, I now have 3 over 10,000. That number is 0. This whole number is almost 0. So anytime my x gets bigger, my number as a whole gets much, much, much smaller. And this guy is 3 10,000ths, 0.0003. So when I only plug in 10, imagine what would happen if I plugged in like 1,000. Our number is basically going to be 0. So whenever we ask for the limit as x approaches either infinity, positive infinity, or negative infinity, and it doesn't matter what we have up here. So if I had x to the third up here, blah, 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 x to the fourth down here, blah, 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 blah. Whatever's going to happen is whenever your x is more dominant in the numerator, the denominator, you are always going to hit 0 when your limit approaches either infinity. So that's the end behavior. Okay, when the degrees are the same, the limit as x approaches infinity is going to be the ratio of the leading coefficients. When you have a case like the last one, when the upstairs is bigger than the downstairs, you're going to head towards one of the infinities. And in this case, when the downstairs is bigger than the upstairs, you're going to head towards zero no matter what. So before we actually start doing some examples, let's talk about wholes and multiplicity. Now, we know that if I were to do something like this, okay, we should expect crazy things to happen at 3 and 5. Well, what if I added this to it? Whenever one of your factors in the numerator is the same as a factor in the denominator, what happens is the behavior of the graph is going to be as if these were crossed out. So the graph behaves like 1 over x minus 5. However, x still can't be negative 3. So regular 3. So what's going to happen is you might have a graph that looks something like this, but at positive 3 you have a hole and it keeps going. Okay, so whenever the numerator and the denominator are exactly the same, expect a hole to exist there. Even though the graph acts as if it didn't exist in the first place, we're still not allowed to plug in 3 because of the original problem being what it is. Now, let's just say that somewhere in the problem, I have something like this, x minus 2 squared. That implies multiplicity. Now, what we had up here is we were expecting things to go wacky at regular 5, which makes my picture not accurate at all. That hole should have been over there, but you get the idea. This wackiness happened at x equals 5, mainly because x is not allowed to be 5. However, when you have an even multiplicity creating an asymptote, what's going to happen is these guys go up in the same direction. So at 2, these guys are going to go up in the same direction. Maybe they go down in the same direction. It all depends on what's going on up here and anywhere else. But when the multiplicity is even, both lines go up or down in the same direction. Now, similarly, if I were to give you a problem like this, right, where I have multiple multiplicity things going up here, and then multiple multiplicity things going on down here. Okay, the same rules apply. It takes on the behavior of something like this, and we still see action like this happening on our graph. Okay, so rationals are weird. They give you weird graphs. And we obviously have a lot going on with these types of problems. So I think we can now start doing some problems. All right. Just kidding. Working backwards. Lots of problems are going to give you something like this. Let me give you something where the degree of the numerator is 2 and the degree of the denominator is also 2. I don't know why I put 3 there. And let's just say that there is a vertical asymptote at 3 and a hole at 4 and a 0 at 5. We can create a rational function. If the vertical asymptote is 3, that means it explodes at 3. Now, what's a factor going to look like if it explodes at 3? X minus 3, because if I plug in 3, 3 minus 3 is 0. If a hole exists at 4, that means I have the same exact thing up here that I have down here, and all the action happens at the opposite, x minus 4. If a 0 occurs, that's going to happen when a factor in the numerator gives you a 0, so x minus 5. So that would be an example of something like that. So now, I think we can go over a few problems. All right. So based off of what we learned, f of x equals numerator, denominator. The degrees are the same. I have a factor with an x, a factor with an x, so x squared upstairs, a factor with an x, and a factor in an x with an x, x squared downstairs, x squared, everything's the same. Find the zeros. We find the zeros by taking the numerator and setting that equal to 0. So x minus 5 times x plus 9 equals 0. 0 product property. X equals the opposite of x minus 5 and the opposite of x plus 9. Okay? Pretty simple. The vertical asymptotes. Since nothing upstairs and downstairs repeats, my vertical asymptotes exist at the opposite down here. So where does x plus 3 and x plus 4 equal 0? Well, the opposite of plus 3 and plus 4, which one of my vertical asymptotes is going to be negative 3, and the other vertical asymptote is going to be the equation x equals negative 4. I'm writing it out like this because they're both equations, whereas these guys are x values. What is the horizontal asymptote? Well, the horizontal asymptote exists at the end behavior. So by doing C, we do D. And for some reason, I have a second C. Great. What is the horizontal asymptote? Well, let's answer first C and D at the same time. The way we find the horizontal asymptotes is the same way as finding the limit as x approaches infinity. What you need is the leading term. Well, I don't have a leading term, but there's a shortcut. Always take the leading term in each factor and multiply them together. That will give you the leading term for the numerator. Do the same thing. Multiply the leading term of each factor. That will get you the leading term here. I don't care about anything else. So my concern is x squared over x squared, which becomes 1. So what happens when we plug infinity into x? Well, there is no x. I just get 1. So the limit as x approaches infinity is 1, which means my picture, whatever it looks like, is going to end up flattening out at 1. Okay, and the same way. So a horizontal line that flattens out at 1 is going to be the equation y equals 1. Okay, so we killed 2 birds with 1 stone, and we're about to kill a third, because what is the whole? Well, the whole exists when you have a factor in the denominator that's the same as the numerator. We don't, so there is none. Nowhere. Fun. Love these. Love them. Love them so much. Find the zeros. All right. Now what I have to do is I have to, looks like factor everything out. So I'm going to pull out an x upstairs. So that leaves me with x squared minus x minus 6. In the denominator, I can factor that, difference of squares, x plus 4, x minus 4. I can continue factoring the top because this is going to factor out to x minus 3 and x plus 2 over x plus 4, x minus 4. All right. Find the zeros. My zeros exist wherever the numerator is set equal to 0. So x is going to equal 0. X minus 3, positive 3, x plus 2, negative 2. Find the vertical asymptotes. Nothing upstairs and downstairs repeat. Nothing. So my vertical asymptotes are wherever my denominator is set equal to 0. So x minus 4. So that's going to be negative 4. X equals negative 4. And also the equation x equals positive 4 because it's the opposite of these numbers in here. Find the slant asymptote. The slant asymptote, whenever your denominator is greater than the numerator, is going to be when you divide that from that using long division, polynomial long division. So let's do polynomial long division. X squared minus 16 divided by x cubed minus x squared minus 6x plus 0. And if you're wondering, do we have to put the plus 0 there? You do. I think you do. Maybe I'm wrong. We'll find out. X times what is x to the third? I'm sorry, x squared times what is x to the third? X squared, oh, you know what I forgot? Oh man, this would have derailed the whole thing. I'm missing an x here, so I have to write out x squared plus 0x minus 16. That would have ruined everything. Here I am talking about, do I have to do this? And I forgot about doing this. Shame on me. X squared times what is x cubed? x squared times x is x cubed. Multiply x to everything. X to the third, 0, negative 16x. Subtract this guy, which means flip the signs and bring it down. You go away. Negative x squared minus 0x squared is negative x squared. Negative 6 plus 16 is positive 10x. Drop down the plus 0. Okay? X squared times what is negative x squared? Negative 1. Negative 1 times x squared is negative x squared. Negative 1 times 0 is 0x. Negative 1 times negative 16 is 16. Flip the signs on everything because you're subtracting. So plus, minus, minus. You go away, and you're going to be some remainder. Now, who cares? Who cares? Because this guy gives me the equation of the slant asymptote. So my equation of the slant asymptote is y equals x minus 1. Find the limit as x approaches infinity. So I'm going to go back to the original problem. I'm going to pretend you guys don't exist. So the limit of x cubed over x squared, okay, is the same thing as saying the limit as x approaches infinity of x. What happens when you plug infinity into x? You get infinity. So I'm expecting this picture to basically, I don't even want to draw it. I'm going to pretend. X might probably something like this without drawing it. Okay. Oh, that's going to look so bad. No, that's not even right at all. Yeah, see, I don't want to do it. I don't want to do it. I don't want to do it. Let's just pretend that I was drawing a road. All right, next problem. Oof, gross. All right, so I have x to the b times x plus 2 times x minus 4. Find an integer b that would give f of x a horizontal asymptote of y equals 1. Okay, so we have to be careful here. Horizontal asymptotes live where your limit approaches infinity. Okay, so if I were to give you an example like this, if p was bigger than q, okay, so there's 3 situations where p is bigger than q is bigger than p, and p equals q. So let's use common sense. If p was bigger than q, that means this guy is greater than that guy, which means that has more x's than that, which means I'm going to approach one of the infinities. So this is not the option that we would use. When q was bigger than p, that means I would have like x to the 5th, and maybe up here is x squared, and this approaches 0. So in a case like this, I need p equal to q. So I need p equal to q. I have one leading x, another leading x, so that's 2, and my leading coefficient down here is x to the 5th. So in order to make this match up with that, I have 2 x's up here, I don't know, has to match with 5 x's down here, b has to be 3. Because when that's x to the 3rd, and I multiply all this out, I have a leading coefficient of x to the 5th, which matches up with x to the 5th. Great. Find any vertical asymptotes. Well, let's bring out x cubed. That leaves me with x squared minus 9. By the way, I'm factoring out the bottom, the denominator. Okay, I can factor that further. X to the 3rd is going to equal, is going to be multiplied to x plus 3, x minus 3. So times x plus 3, x minus 3, and that gives me 3 vertical asymptotes. Triple multiplicity at 0. The opposite of 3 is negative 3. And the opposite of negative 3 is, ooh. And look at me being foolish. Since I pulled out an x to the 3rd and I made upstairs x to the 3rd, I have x to the 3rd up here and x to the 3rd down here. Find any holes? Holes exist at x equals 0. I don't have any horizontal as a vertical asymptote at 0 because since I have x cubed upstairs and x cubed downstairs, they cancel each other out. And the whole thing here ends up having a behavior of an equation like x plus 2 times x minus 4 over x plus 3 x minus 3. And since I had x cubed out here and x cubed out here, my holes exist there. And I don't have a vertical asymptote at 0. Whew. Oh, dodged a bullet on that one. Find the limit as x approaches infinity. All right, well, multiply u to u and multiply u to u, and I get x squared over x squared, which equals 1. Phew. These problems are tricky, and you need to be a little careful on them, because I was not careful with this guy right here. This is stupid because I created these problems. I should be a little bit more careful. Rewrite f of x as one fraction. Ooh, I hate these. So what we're going to do in order to rewrite it as one fraction is we're going to, let me rewrite the first fraction, give myself some space. I need a greatest common denominator. Nothing in common. So I just need to multiply this guy by x plus 1 over x plus 1. And I need to multiply this guy by x minus 4 over x minus 4. I'm going to keep the bottom factored. So x plus 1, x minus 4. Upstairs, if I do distributive property, I have 2 times x, 2 times 1, negative 5 times x, be careful, negative 5 times negative 4. And then these guys combine to make negative 3x plus 21 over x plus 1x minus 4. All right, done. Find the x values that make f of x equal to 0. Well, if f of x was equal to 0, this is the same thing as me finding the zeros. So who cares what that is? Because I'll just multiply that to 0 and it'll go away. So what I need to do is do negative 3x plus 21 equals 0. Subtract 21, so negative 3x equals negative 21. Divide by negative 3, and the only x value that would make f of x equal to 0 is 7. Okay. Just doing the math over here. Oh, it's gross, but yeah, that works. Find the limit as x approaches infinity. Okay, so if I were to look at this guy here, I have negative 3x as a leading coefficient. Okay, this has to do with u. Negative 3x as a leading coefficient over x times x, which is x squared. That simplifies out to negative 3 over x. And as x increases, as x gets larger, we are going to hit 0. So the limit as x approaches infinity is 0. Where is f of x undefined? At 4 and negative 1. That was kind of friendly. It's kind of easy one finally. Until we hit this. Estimate the rate of change on the interval negative 1,000 over 1,000. Well, hold on. If the limit approaches infinity is 0, that means my graph is going to be like way over here at right around 0. So like if I were to plug in like 1,000, I'm going to get 0. Similarly, if I were to go to negative 1,000, I mean, no matter which infinity I plug in, this is still going to be 0. So this is basically going to be 0. So the rate of change would be, what's the difference between 0 to 0? Oh, that's why it says estimate. Oh, I should have known. Oh, me, creating fun problems. Yeah, the last thing you want to do is plug in 1,000. But even if you did, let's just have fun and say you did. If I plugged in 1,000, I would get 2 over really big number minus 5 over really big number, basically 0 minus 0. And if I plugged in negative 1,000, I would basically get 0 minus 0. And so 0 minus 0 is 0. That's fun. That's fun. Multiplicity everywhere. Find any vertical asymptotes. Well, okay. Okay. I can do this. Now, let's ignore that problem for a second. Find any holes. See how these guys are the same exact denominator? Holes are going to exist at negative 4. Now, here's the thing. It's not going to exist at 1 because what's going to happen at 1 is since I have more x minus 1s in the denominator that I have in the numerator, it's going to take on the behavior of 1 over x minus 1 to the third. Okay, so it's going to take on that behavior, not giving me any holes there. And so I'm going to have a vertical asymptote at x equals 1. These guys crossed out. That's what gave me holes. They completely crossed out. You crossed out and left me with 3, and the whole thing ends up looking at that like that. So holes are at negative 4. Vertical asymptotes are at positive 1. So my equation now looks like this, where I'm not allowed to plug in negative 4 or 1. Since I have a much more powerful denominator, all right, if I were to take this and multiply that to itself 3 times, it follows the behavior of 1 over x cubed. Okay, and when you multiply, or not, don't even do that. When this number gets much, much, much bigger, whenever you have 1 over or 3 over or a number over x to the who cares, it's always going to equal 0 because in this case, the denominator is greater than the numerator. Find the zeros. Ugh. All right, well, let's factor that. I can bring out a 2x, and that's it. That leaves me with x squared plus 4x plus 4. Ooh, a perfect square trinomial. Over difference of squares, x minus 3, x plus 3. So now you become 2x, x plus 2 times x plus 2, which is x plus 2 squared. Multiplicity. Multiplicity. This becomes x minus 3, x plus 3. So nothing fancy happens. No holes, so I don't have to worry about that like I saw in a previous problem. Find the zeros. Well, the zeros exist whenever the numerator is set equal to 0. So what happens when 2x is equal to 0? Divide by 2, you get 0. X plus 2 is equal to 0. Subtract 2, you get negative 2. Find the vertical asymptotes. That exists whenever the bottom is set equal to 0. So vertical asymptotes are the equation x equals 3 and the equation x equals negative 3 because they're the opposite of that. Find the slant asymptote. Well, since this guy's bigger than that guy, I'm going to have myself a slant asymptote. So let's do x squared minus 9. But I have to remember 0x minus 9. Not going to make that mistake again. And I'm going to divide the original guy here. 2x cubed plus 8x squared plus 8x plus 0. X squared times what is 2x cubed? 2x. Okay, multiply 2x to this whole thing. 2x times x squared is 2x cubed plus nothing, x squared. Minus 18x. Okay, flip the signs. Minus, minus, plus. You go away. You become 8x squared. You become, that is a minus, so it became a plus. I was just making sure I did it right. 26x, not that it matters, plus 0. X squared times what gives you 8x squared? Plus 8. 8 times x squared is 8x squared plus 0x minus 72. Not that it matters because you go away. I don't care about remainders. The slant asymptote is the line y equals 2x plus 8. All right. I have to take another break. This last one, I may have included one that's just a bit too bonkers, but we're going to do it anyway. I'm not sure if you'd see one this crazy on a no calculator portion, but like I said, let's give it a shot. I'll walk you through everything. I'm now asking you which part of this graph is going to be positive. So let's just try to break it all down. Okay, let's just try to break it all down. Let's find out where the limit is, all right, as x approaches negative infinity. And let's find out what the limit is as x approaches positive infinity. I'm going to try to put together a very marginal graph to help me figure stuff out, see what happens. Remember, when you're trying to find the limit, you're going to take the leading term over the leading term. Nothing else really matters. Okay, so in both of these cases, the only thing that really matters is the fact that I have 2x cubed over x squared, which simplifies to 2x. If I plug in negative infinity, 2 times negative infinity is negative infinity. Similarly here, 2x. If I plug in infinity, it's going to be infinity. So I know that all going to the left, this guy is heading downward, going to the right, this guy is heading upward. What else do I know? Well, zeros are at 0 and negative 2. Now, I put a b up there before I started recording for some reason, because since the multiplicity at negative 2, where is it? There you are. At negative 2 is 2, it's going to bounce. So action happens at the zeros, and what's going to happen is a bounce here. Now, what else do I have? I have stuff going on at asymptotes, which occur at negative 3 and positive 3. So let's recreate, let's recreate a very possibly inaccurate graph of what this is going to look like. Action happens at negative 3, negative 2, 0, and 3. So negative 3, negative 2, 0, and 3. That's where the action happens. Okay. Now, my zeros are at negative 2, which means whatever happens, nothing crosses the x-axis until 0 and negative 2. Negative 3 and positive 3 are asymptotes. So since my limit as x approaches negative infinity is also negative infinity, and I have a change happening at negative 3, I have an asymptote at negative 3, this guy is going downward. But what also happens is this guy becomes an asymptote. Now at negative 3, I have a regular looking asymptote, no multiplicity. So since there's no multiplicity, this guy is going to reappear up here. At negative 2, I bounce off. So I'm going to go to negative 2 and bounce. I'm going to come back up. At 0, I go through. And then I'm going to go downward. At positive 3, I have an asymptote. Since the multiplicity is 1, it reappears up here. And since the limit is positive and I'm not crossing the x-axis, it's going to look like this. So let's erase all of this mess over here. Okay, sorry, long division, but I'm erasing you. And let's make ourselves a sine graph. Again, will you see a problem this crazy on AP Precalculus in the no calculator section? I don't think so. This problem is insane. I think when I created it, I just wasn't thinking, and I just made things difficult for me. Action happens at negative 3. Action also happens at negative 2. Action happens at 0, and action happens at positive 3. Okay? From negative 3 and on to the left, it's underneath, so it's going to be negative. I'm just going to write it out. I'm not going to try to draw it like I've done in the past. From negative 3 to 2, it's positive. From negative 2 to 0, it's positive. From 0 to 3, it's negative. And I accidentally erased this chunk right here. And from 0 or from 3 to infinity, it's positive. I care about where this stuff is positive. So it's positive between -3 and 0, but I'm not allowed to include -2 because it hits -2. So I will say that between -3 and -2 is positive, union. Between -2 and 0 is positive, union. And from 3 on to forever, it's positive. Awful, awful, terrible, terrible problem. I'm sorry. But I think this is the last one coming right up. And it's not. A rational function in the form p of x over q of x has the traits of the graphs shown below. Create a function that has a hole at 3 and a vertical asymptote at -4. All right, q of x appears to be a quadratic, so the degree is going to be 2. P of x appears to be linear, so the degree is going to be 1. All right, so let's start out with the hole. If I have a hole at 3, that means down here I have x minus 3, and up here I have x minus 3. And if it has a vertical asymptote at x equals -4, then down here I have x positive 4. The quadratic is degree 2. There's 2 x's. And the linear is degree 1. There's 1x. And I'll just throw an f of x in front of it, and that should do it. Not bad. Not bad. I like it. I can appreciate that problem. Now we're at the last one. Now, this is a calculator problem. Okay, look at it. Use the calculator to do this whole mess. So I'm going to use the calculator to do this whole thing. Find the zeros. Okay. All right, we have a crazy fraction we have to graph, so let's hit y equals and graph it. What I'm going to do is make sure that my entire numerator is in parentheses. So I'm starting out with an opening parentheses, and I have to make sure that I close it. So double parentheses here is done on purpose. My x value is right here, so click that, plus 2, close it. And then I have x minus 5, close it. And then I have a quadratic, so x is right there, squared is right there, plus 1.5x, plus 1.5x, minus 67.5, bada bing. And since I started out with a big left parentheses, I have to make sure I close that parentheses. Now the entire numerator is wrapped in parentheses. Hit divided by to create your fraction bar. I'm going to do the same double parentheses to do the numerator because I have a bunch of stuff going on down there as well. Denominator, I think I said numerator. Whatever. No one's paying to hear me speak. X minus 4. Now, don't forget to square it. That's going to give us some multiplicity. That'll show up later on. X plus 7. And x plus 2. Ooh, so an x plus 2 in the numerator and the denominator. I wonder if that'll show up. Now, let's hit graph and see what I end up with. Now, our first job is to find the zeros. The zeros exist whenever the numerator is set equal to 0 and you solve. I'm factoring a bunch here, except that I didn't factor that part right there. I have a feeling that wherever x plus 2 is, it's not going to work out. Because I have an x plus 2 in the denominator, it's going to create a hole. But I expect a 0 to exist at 5. This right here is gross and it wasn't factored for me, so I'm assuming it's going to give me zeros that would be like me factoring that. So let's find the zeros. The way you find the zeros is you hit second, calc, and then either hit 2 or go down and hit enter, and then zeros. I'm expecting a 0 right there. I'm expecting the 0 right there, and I'm expecting the 0 right there. So let's go left to right. I'm going to hold down the left button, and I'm going to make sure my cursor is to the left of where my 0 should appear. So since I'm assuming it looks like it was -9, my dot is blinking in the positive y range. I'm going to hit enter. I'm going to go to the right until my y has a sign change or until I cross the x-axis, which is what I did. I know I did because it was at positive, now it's negative. Hit enter. My 0 should be in between these two areas. Hit enter again. and it gives me a 0 of -9. So then we repeat the process. Second, trace, go to 0, and we're going to go all the way to the right until we end up to the left of what appears to be around -5, give or take. It could be something different, but if I recall, one of my zeros or one of my factors was x minus 5, so I'm expecting this to be regular 5. So hit enter since we're on the left side. Let's cross sides, hit enter again, always hit enter for guess. There's my 0 of 5. Let's do it one last time. Second trace, 0. Let's move my cursor to the right a little bit. To the right. Cupid Shuffle. Remember him? Someone told me the other day that he's in jail, and I don't believe it. Anyway, I crossed the x-axis. Let's hit enter. And by hitting enter through guess, I have a 0 of 7.5. So my zeros were at -9, 5, and 7.5. So if I look at this, the 5 makes sense. The -9 and the 7.5 must come from this gross-looking quadratic right here. And if you're wondering, well, what about that, what was it, x plus 2? Why did we go through -2? Because there's an x plus 2 on the bottom. We'll deal with that in a second. Oh, terrific. I wrote it down here somewhere. The zeros are -9, 5, and 7.5. What coordinate does a hole exist? Oh, this one's going to be fascinating. I wonder how it's done. Hey, remember a few seconds ago when I said we're going to deal with this in a few seconds? Well, here we are. What I need to do is I need to find where the hole exists. Now, I have x plus 2 on the top and x plus 2 on the bottom, which means my hole exists at -2. Now, here's the thing. You might be thinking, well, why don't we plug in -2? Well, if I plug in -2 into this denominator here, it's going to be undefined. Let me demonstrate that. Hit second trace and go to value. This allows me to find the exact value if I type in -2. So -2, enter. See how it says y equals blah? That's because there's no blah. And I did not say blah, blah, blah. I just said blah. So what I want to do is, since I can't plug in -2, let's plug in -2.001. Much better. That gives us 2.5869. So let's write that out. 2.5869. Now, some of you purists might be like, well, since we tried it one space to the left, why don't we try it one space to the right? Good idea. Let's plug in -1.999. So value, -1.999. Hit enter, and I get 2.5861. So since I got 2.5869 and 2.5861, let's settle on a final answer that is somewhere in between at 2.5865. Oh, magnificent. Magnificent. So the coordinate is going to be -2, 2.5865 as clearly seen. That is an 8. Ugh. All right. Find the limit as x approaches -infinity. Let's find the limit as x approaches -infinity. Well, I really can't see where -infinity is, and I can't see where that's going. So let's do this. Let's create a new window where I want to see what happens at like -infinity. My x-min is at -10. That's not even close to -infinity. So let's set it to -10, 1, 2, 3, 1, 2, 3 million. -10 million, it's a pretty big number. So if I hit graph, straight line. But where is that straight line? Well, let's do the value thing again. Now that I changed my window, I can actually find out what the value of -10 million is. And when I hit enter, I get y equals 1.00000. Oh, you know what? 1.00000 is probably 1. So I'm going to go with that. Now, if you were thinking, sir, when it looked like this, why didn't you just plug in -10 million there? Because it doesn't let me plug in a value unless the calculator sees it on the screen. So I have to change my window in order to make that work. Oh, okay. I probably didn't need a calculator for that, but here it is. It's 1. And find the limit as x approaches 4. Well, that's a new problem. I wonder how we could use a calculator to do it. All right, last but not least, let's see what happened when my limit hits 4. Now, here's the problem. Problem number 1. I can't plug in 4. Why? Well, x minus 4 lives in the denominator. And if you recall, there's a multiplicity of 2. So here's a fun fact. If I were to ask you where the limit of negative 1, 2, 3, 4, 5, 6, 7 is, if I were to ask you what the limit of negative 7 is, since this guy at negative 7 is going up and this guy is going down, there is no limit. The limit does not exist. Mean girls. However, whenever you have a multiplicity of an even number, my graph goes in the same exact direction on both sides. So when it asks me to find the limit as x approaches 4, since the left side is going up and since the right side is going up, they're both going up to positive infinity, which means the limit of regular 4 is going to be positive infinity. Oh, great, infinity. Well, this hopefully covers those 4 sections. A couple hiccups along the way, a couple stutters along the way, but again, I'm a math teacher. Don't expect me to speak good. Thanks for watching. Don't forget to like and subscribe, and I love you so very much. Bye. What up, what up? Let's finish Unit 1 of AP Precalculus, shall we? We're hitting the last 4 sections, lots of modeling, kind of like what I did in college to pay the bills. And let's just jump right into it. The first thing that we're going to see is the binomial theorem. Now, what's the binomial theorem? Well, let's just say you have a binomial, like x plus 7. And you want to take that parentheses and write it out to the 8th power. And you're like, whoa, that's a lot of foiling. More foiling than if I worked at a fancy restaurant. I agree. So thankfully, we have the binomial theorem to help us get by. Now, the binomial theorem uses what's called Pascal's triangle. All right, you start out with 1 up here, and then you put a 1 here and a 1 here. And then from here on out, whatever number's on the outside is just always going to be 1. But whatever number is in the middle is going to be the sum of these guys. So you would be 2, and you would be 1. And you would be 1. And 1 plus 2 is 3. And 2 plus 1 is 3. And 1 is on the outside. And you put 1 on the outside. And 1 plus 3 is 4. And 3 plus 3 is 6. And 3 plus 1 is 4. I struggled with that one there. And 1. And then you could keep going and keep going. Now, why does this matter? Well, the binomial theorem follows this interesting pattern where if you have a polynomial, or if you have something in the form x plus y, actually, you know what? I prefer to do a plus b. Let's do a plus b. I like those letters. Let's do that. If you have something in the form a plus b to the a power. No, we can't use a. Let's use the d power, d for degrees, to the d power. If the d is 0, you're going to use this guy, and we would never use that guy. If the d was 1, if the degree was 1, we would use u. In other words, a plus 1. We would use this for degree 2. We would use this for degree 3. We would use this for degree 4. Now, what this looks like is if I were to give you an example like x plus 9 cubed, okay? That's going to follow that row right there, okay? Now, the binomial theorem states that for a plus b to the third, what you're going to write out is you're going to write out a to the third. So actually, invisible 1, a to the third, plus 3, a squared, b, see what we're doing, plus 3, a b squared, plus 1, b cubed. All right, what we do is we start out with that value, we have it peaked out at the degree, and we move it down until we get to nothing at the very end. And on the way to the right side, we peak that out at 3, and we move our way to the left until we get to the very end, and these numbers are our coefficients. So if this was something like a plus b to the fourth, it would follow the same rules. Let's get some different colors. You would have 1a to the fourth plus 4a to the third b plus 6a squared b squared plus 4ab cubed plus 1b cubed. Now that takes us back to this guy right here, okay? Knowing that we're going to use this, what is that going to look like? Well, I will label you A and I will label you B. So I shouldn't have used 9. It's too late. I've already committed. I'm going to write out 1x to the third plus 3 times x squared times b, okay, see what I did, plus 3 times x times 9 squared plus 1 times 9 cubed. And then it's just a matter of simplifying. I don't need 1 in front of x cubed, okay? 3 times 9 is 27, 27x squared, plus 3 times 81 is going to be 243x. 9 times 9 times 9.
It's 729.
I knew that. Okay? So that right there, boys and girls, is the binomial theorem in action. Next thing that we're going to look at is transformations. Now, if I were to take this picture right here, okay, and move it down and over, of course with the arrow there, that's called a transformation. Okay, there's 4 main types of transformations that we're going to deal with. Transformation type number 1 is going to be a vertical translation. Okay, a vertical translation. Translation is movement and movement only. If I give you f of x, right? So f of x equals some quadratic like that. And then all of a sudden I give you a new one and say, all I want you to do is add 3 to it. That is a vertical transformation. The positive 3 means you move up. If it was a negative 3, you'd move down. Similar, if I have a horizontal translation, this is similar but gross. If I give you f of x, if you throw a negative inside the parentheses with the x, next to x, okay, like this, and this is what's going to annoy you, if it's negative, you move right. So negative means moving right. Positive means moving left. It's opposite land whenever you're working within the parentheses. That's just the way it is. That's just the way it is. According to Tupac, things will never be the same. Okay, Changes. Great song. Great song. Rest in peace, Tupac. Too young. I mean, a lot of people think he's still alive, but who knows? All right, now we're going to talk about a dilation. A dilation is when your shape stretches, widens, whatever. Okay, and there's a couple types of dilations. Now, the first one is called the vertical dilation. Okay, a vertical dilation is basically you're taking your shape and you're squeezing it depending on what's going on. The way you do that is you take some number and you just multiply it to your whole f of x. And what that looks like in this case is this gets skinnier. Okay, this gets skinnier. It's also called a stretch because when it gets skinnier, what it looks like if it's a vertical dilation is if you were to take your parabola and like grab it from the top and pull it. And so what happens is by pulling it, it goes like this. And so that's the vertical dilation. If this number is in between 0 and 1, it is also a vertical dilation, but it's called a compression. And what that looks like is if I give you a parabola and squeeze it downward, that's a compression. It makes your thing look wider. So a vertical dilation is when you have a number multiplied to the whole function. Now, if I were to give you a horizontal dilation, the way you handle that is very similar to the horizontal translation, and you only multiply the x by a number. Okay, so f of x, and this is, oh man, this is going to be fun. You ready? F of 1 over like a number, x. Okay. And by putting it 1 over a number, by 1 over a number, you are saying if it's 3, 1 over 3, you are doing a horizontal stretch of 3. Whereas if it was regular 3, it would be a horizontal compression. Okay? So the wording is weird. It's not pleasant. Again, I highly suggest you watch videos on this stuff because, the wording is not pleasant, but, it is what it is. Now, we know linear, quadratic, and cubic models. We've done this before, but let's just bring it all back. A very common question is I give you a chart, whether it's a T-chart that looks like this. I'm just going to use these numbers that I quick whipped up, so sorry for looking off to the side. Very unprofessional of me. -6, -5, -4, 3, 22, the Taylor Swift special, and 59. Okay? Now, a very common question is find a model that best fits the data. All right? So we're thinking, all right, well, is it linear, is it quadratic, or is it cubic? Let's do the rules. If it's linear, all right, all of these go up by the same number, consecutive equal length input value intervals. I got it. I said that phrase and I said it correctly for once. Okay. What am I doing over here? Well, to go from -6 to -5, I add 1. To go from -5 to -4, I add 1. To go from -4 to 3, I add 7. To go from 3 to 22, the Taylor Swift special, I add 19. And to go from 22 to 59, I add 37. Definitely not linear. Okay? Definitely not linear. And in this case, it's not concave up. See, I look at this as like rate of change. My numbers aren't increasing right away. So this tells us that it's probably not going to be quadratic either. But we don't know that. We don't know that. I'm going to pretend that I didn't say that. Let's test for quadraticity. And the 100% is not a word. Add nothing. Add 6. Add 12. Add 18. Are these numbers the same? Are the rates of change the rate of change the same? No. So it's not a quadratic either. So let's see if the rate of change or the rate of change or the rate of change is the same. And oh, happy day. You add 6 in every time. Uh-oh. Not even Catholic. It's cubic. So a problem like this, you'll often see determine a model that best fits the description. Now that I know it's cubic, I can answer questions like this. Now, with questions like this, let me move my face. We are going to use the calculator. In a previous video, when I do the thing where I put the calculator on the screen, it somehow like cancels out my voice sometimes. So I'm not going to do the thing where I go like this and look at the camera. I know you, all 12 of you who watch these, find that so funny, but that's not what I'm going to do. I'm just going to split screen right now and show you how to do the linear regression, quadratic regression, and cubic regression of each of these. Let's start out with linear. All right, let's talk about linear regression, quadratic regression, and cubic regression. All processes are done pretty much the same way. Whenever you're asked to input data, you're going to go over to Stat, hit Stat, and go right to Edit. It gives you all of these lists. Right now we're focusing on two lists, L1 and L2, and we just start typing things in. I can probably get away with using my keyboard, so I'm going to do that and hopefully not make a mistake. All right, so you just make sure you type in your number, hit enter every time, move to the right, and do it again. So we have 3, 11, a terrible band, 19, 27, and and 35. Right now we're going with the known fact that this is linear. I know this is linear. You know, in the previous slide, we talked about how to tell if it's linear, quadratic, or cubic. In this case, I know it's linear, so I'm going to find the linear regression. So I'm going to always quit by doing second mode. That step might not be necessary, but at the very least, I'm out of where I need to be. To do linear regression, hit Stat, go over to Calc, and find linreg. Now, if you see the other linreg, this is more for statistics. This is more for algebra, calculus stuff. So we're going to go with 4. So you can either hit 4 or go down to 4 and hit enter. We need to calculate, so you can just hit enter a bunch of times and calculate. And it gives you y equals ax plus b, where a is 4 and b is 3. So the way we recognize this is you write this out. Okay, slope-intercept form, where instead of a you have, or instead of m you have a, and you just substitute this in. So our final answer here that I'm going to write out in a second is y equals 4x plus 3 linear regression. All right, so the linear regression gives us y. The linear regression gives us y equals 4x plus 3. All right. Let's take a look at quadratic. All right, let's do quadratic regression. Now, if I were to go and do the same thing, I'm going to purposely do this, hit Stat, hit Edit, and I still have the data from my previous problem. Now, the data that I'm going to use is completely different. So if you're using like a school calculator, or in my case, I'm using this calculator that I have online, you can clear your calculator by doing second plus 712, and that clears everything, okay? So that's out of the way. So let's pretend that never happened. Let's do quadratic regression. I have to input values. So go to Stat, go to Edit. You have your L1 and your L2, just like we did with linreg. And we're going to type this in. Now, I can't get away with typing it using my keyboard, because if I were to use the negative button, it thinks it's the minus sign. And the only place ever that I've noticed in all of my life where there's a difference between a minus sign and a negative button are these TI calculators. Get your act together, Texas Instruments. So I have to actually, compute this in. -3, enter. -2, enter. -1, enter. And now I can just type the rest in. 0, enter. 1, enter. 2, enter. 3, enter. Then you go to L2 and you type those values in. 2, 0, 0, 2, 6, 12, 20. Now, we already know that this is quadratic, so we don't have to worry about finding out which one it is. We're just learning how to use this, or reteaching how to use this. So I'm going to quit second mode, and the process is almost the exact same as linreg. Go to Stat, go to Calc. Instead of linreg, go to quadreg. So you can hit 5, or you can go down to 5 and hit enter. Go to calculate by hitting enter a bunch of times. Once you hit calculate, you get exactly what you need. So you have what's the standard form of a quadratic equation, y equals ax squared plus bx plus c. A is 1, so replace that. B is 3, so replace that. C is 2, so replace that. And at the end, we should have y equals x squared plus 3x plus 2. That's our quadratic formula. Quadratic regression gets us y equals x squared plus 3x plus 2. Same exact process as this one. Let's go to this guy right here, cubic. Cubic Red, or Cubic Reg, or Cubic Frog, which is a company that makes toddler games. I would know, I have a toddler. If I hit Stat, Edit, just like I did last time, there's a mess there. So it wouldn't be the worst idea to hit second plus 712 to clear anything. Now, if you have your own personal calculator and you have stuff saved, you don't want to do this, but this is from the internet, so I don't care. Hit Stat, hit Edit like we did last time, and type your values in. Okay, 0, 1, 2, 3, 4. And I can get away with using a keyboard because I don't have to worry about negatives. 2, enter. 3, enter. 10, enter. 29, enter, and 66, enter. So the numbers change, and they change a lot. We know this is cubic. Don't have to worry about adding and finding rates of change of rates of change of rates of change. We're just going to quit out of this by hitting second mode. Go to Stat, Very similar as the last two, go to calc, but instead we want cubic reg, and it gives you a general form after I hit calculate. And there it is. So this is where it gets a little interesting, and we just have to be a little careful. Keep in mind that, TI is not flawless. You already heard my great meltdown of the minuses and the negatives, but that is what a cubic looks like. You got x to the third. So I would write out y equals 1x to the third, but actually not write out the 1. What is this? Well, this has negative 4.2 e to the negative 12. Well, e means times 10 to the. So if you've ever used these, if you ever use like scientific notation, this is scientific notation. And what this number is negative 0.00000000, like 11 of them for 2. And 0.00011 of them for 2 is going to be 0. So whenever you see e to the negative something like this, assume it's 0. So A is 1, B is nothing, C is nothing, D is 2. So basically we're eliminating both of these middle terms, and we're going to be left with y equals 1, or just y equals x cubed, skip, plus D, and D is 2. Y equals x cubed plus 2, cubic regression. Y equals x to the third plus 2. Those e's are weird, but if you see them now, you know what to do. All right. Right off the bat, find x or f of x, which is, binomial theorem. Now, we saw from earlier that binomial theorem requires Pascal's triangle. This is x to the fourth. So this is degree 0, degree 1, degree 2, degree 3, and degree 4. I'm going to label you A, I'm going to label you B, and let's just get right to it. 1a to the fourth is 1x to the fourth, plus 4a to the third is x to the third, b to the regular is just 4, plus 6a squared is x squared times 4 squared, a fun game, plus 4. Regular a is just x times 4 to the third is 4 to the third, plus 1 times 4 to the fourth. Okay? 1x to the fourth is regular x to the fourth. 4 times 4 is 16, so plus 16. X to the third. 16 times 6. I'm going to cheat. 16 times 6.
It's 96.
It's 96. X squared plus 4 times 4 times 4 times 4.
That would be 256.
And then the same thing. Yeah. All right. Explain how g of x is a transformation of x or f of x. So I have a 3 in front of my parentheses, not inside my parentheses, which implies that I'm taking f and multiplying f by 3. So be careful. Be careful. What I'm going to do is I'm going to say this. I'm going to pull a 3 out of this whole thing. That leaves me with 3x plus 4 to the fourth minus 4. So what I have is I'm multiplying 3 to f of x. Okay. So let me write that out. Explain how g of x is a transformation of f of x. Well, f of x is x plus 4 to the fourth. G of x explain how g of x is a transformation of f of x. Okay. G of x is 3 times x plus 4 to the fourth minus 12. Well, f of x is x plus 4 to the fourth minus 12, which means g of x is 3 times f of x minus 12. Huh. So what I have is I have a vertical dilation of 3 because 3 lives in front of f of x. So let me say that a vertical dilation of 3 and they want to say, I think I use translation. They might use shift. So vertical translation or shift, whatever wording they use, translation of 12, which means we move 12. So vertical dilation of 3 implies that I stretch it, make it skinnier, and then move it down a bunch. All right. Find the remainder of f of x over h of x. Okay. Well, I found out what f of x was. I have h of x right there. Polynomial long division, baby. So h of x, I don't think I even gave myself enough space. Time to draw small. H of x is this. Ooh, I'm missing an x squared. Make sure you fill that in. X to the third plus 0x squared plus 4x minus 1. F of x ended up being that whole thing. X to the fourth plus 16x to the third plus 96x squared plus 256x plus 256. This is going to be awful. X, actually no, well, it's going to be 2 steps. X to the third times x is x to the fourth. Multiply that x to all 4 of those things, so you got x to the fourth plus 0x cubed plus 4x squared minus x. Flip the signs of everything. Minus, 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 plus. You go away. You become 16, because x to the third times 16 gives me 16x to the third. I jumped the gun. Sorry. Plus 92x squared. Shouldn't you have been? No, I did it right. So plus 257. X, drop down to 256. Ugh. All right. Plus 16. So let's multiply 16 to that. 16x to the third plus 0x squared plus 64 x minus 16. Cross you out. So 92x squared. Oh, flip the signs. Don't want to do that. Don't want to make that mistake. 92 plus or minus nothing is just 92x squared. I think it's 97. Let me just make sure. 157 minus 64.
It's 93.
See, that's why I check. And then this should be 272. So this guy, that one, that guy right there is my remainder. Okay? I could write that out as a factor, but that's going to show up later in this, so I'm not going to. All I had to do was find the remainder. I never said it was easy. I just said it would be fun. Now what this means is this times this gives me this. No, never mind. Let's just move on to the next one. I'm saying too much already, and I'm making myself look stupid. Pretty easy to do. A, what is the domain of f of x? F of x is Rx over Q. Oh, you're Q. So Q would be the denominator. Okay, so the domain is where Q of x is not allowed to be 0. So these guys are not allowed to be 0. Well, let's factor you out and see what you guys would be. You guys add up, the numbers that add up to 7 and multiply out to 10 are 5 and 2. So I wrote that out completely wrong because I've been doing this for a while now. X plus 5, x plus 2, which implies that x cannot be negative 5 and x cannot be negative 2. So if we write this out in interval form, we would say that the domain, you could say, is all real numbers except negative 5 and negative 2, but my domain is negative infinity, also can be written as negative infinity to negative 5, but not including negative 5, union, negative 5 to negative 2, union, and negative 2 on forever. Okay, so the domain is where, or it's everything except for where the function is undefined. The function is undefined when q equals 0. Q equals 0 at negative 5 and negative 2, so q can't be negative 5 and negative 2. List all the zeros, holes, vertical asymptotes, and slant asymptotes of f of x. Okay, so let me write down this whole thing. Okay, now that I have it all factored out. Okay, x plus 2, x minus 4, x plus 5 over, what was it? X plus 5, x plus 2. List all the zeros. The zeros exist when the numerator is equal to 0. So when the numerator is equal to 0, my zeros are going to be the opposite of u. So x is negative 2, the opposite of u, 4, and the opposite of u, negative 5. Now that will change in a minute because holes exist where my factors upstairs and factors downstairs are the same. So that happens at x plus 2 and x plus 5. So my holes exist at negative 2 and negative 5, which means if I were to graph these, right? If I were to graph these, basically this guy takes on the role of just a linear function. So I have to go up here and say, all right, well, if the holes are at negative 2, then a 0 can't be negative 2 because you're not allowed to plug in negative 2. Therefore, you can't get an answer. Same thing. My 0 can't be negative 5 because you're not allowed to plug in negative 5. So my only 0 here is 4. Okay. All right. Good thing I checked, huh? So what are the vertical asymptotes? Well, the vertical asymptotes are where you would have a breakage due to the fact that you have a very what's the phrase, where you're not allowed to use a, I don't know, there's a word and it shows up later here where you're allowed to have, or you can only have the number once in the entire problem. Well, the fact that x plus 5 and x plus 5 is repeated and the fact that x minus 2 is repeated, basically it insinuates that these guys are gone. So what's my vertical asymptote? I don't have any. Kind of weird. It starts with a D. It's going to bother me. Distinct. So since these guys are not distinct, they're indistinct and they're gone, I have no vertical asymptotes. Now, I'm still not allowed to plug in negative 5 and negative 2, but I have no vertical asymptotes. My slant asymptote is found by doing polynomial long division. Now, I have q of x. What I don't have is r of x completely simplified out. Okay, now here's the thing. Life is going to be a little good because you'll expect to see things disappear. We'll get there in a little bit. Actually, no, we'll get there now. When this is graphed, This thing takes on the role of a linear equation that looks like this, where you're not allowed to plug in -5. So -5 over here is a whole, and you're not allowed to plug in -2. It looks like that. So what is the slant asymptote? The slant asymptote is y equals x minus 4. Remember, the slant asymptote is a line that basically goes through whatever polynomial that you have that shows you where the asymptote would be. And since we're only left with an x minus 4, if I were to divide that by that, I would get x minus 4, which makes this guy super easy because this guy, I don't have to do polynomial long division. It's x minus 4. So that's it. I'm done. Oh, how nice. How nice. And I'm super glad looking at this I didn't make a mistake. Otherwise, I'd have to go back and change all of that and do a lot of really frustrating work, and I don't have to. This is where I think we start seeing calculator problems. Maybe it's the next one. This is from like section 11 or section 12, where we'll start to do some word problem-y modeling. This is a very calculus-like problem, okay? I taught calculus for years. I give this exact same problem every single time. An 18-inch by 12-inch regular piece of cardboard paper has X-inch square cuts in all corners to create a box with no lid. Let's draw that out. Okay, let's draw that out. I'm going to draw a rectangle. As you can see, everything is perfect. And according to this, I cut out X-shaped corners, squares out of each corner. In calculus, this is called optimization. Now, we're not going to do as much as you would see in calculus, but you will see a problem like this in calculus. So this is gone. This will now get cut out. This will get cut out. This will get cut out. This will get cut out. Imagine you taking what's left over at here and here and what's left over at here, and imagine folding those up, and you now have yourself a box. Find the equation of the volume of the box. Well, when I fold these things up, when I fold you up along this line and fold you and fold you and fold you, I now have a box with no lid. Okay? Now, when I fold these up, how tall is the box going to be? Well, since I cut out X corners, the height is X. If this whole length was 18, and I just cut out two X's, that X right there, and I cut out X, now my length, if the whole length was 18, the length of this guy, just the part that's left over, is going to be 18 minus an X, so 18 minus 2X. So the length is 18 minus 2X. If you were 12, and I cut out an X and cut out an X, what's going to be left over is 12 minus 2X. 12 minus 2X. Volume is found by multiplying length times width times height. So an equation for volume is X times 18 minus 2X times 12 minus 2X. Okay? Now let's use common sense here for B. What are possible X values that can be used? I'm not going to be like, all right, well, let me try cutting out pieces of cardboard. Let me try out cutting like 10 inches and 10 inches. If you do that, you have no box. At some point, if this whole thing is 12, okay, if this whole thing is 12, you can't cut out 10, because if you cut out 10, you're subtracting away 2 times, you're subtracting out 20 inches. So how are you going to cut out 10? So the largest amount that you can cut, the largest X, is going to be, you go to the shortest side, which was 12. What is the largest thing that you can cut out that would make it disappear? Well, the number that would make this disappear is 6, because 12 minus 2 times 6 is 12. 12 minus 12 is 0. So the largest number that I can cut out is 5.99999, and I still have a little tiny sliver out of a box. So what I will say is I can cut out anything smaller than 6. And you know what? I can cut out anything bigger than 0. Like if I wanted to, I can cut out 0.1 or 0.01 or 0.001, but I can't cut anything that is 0 because there is no cut, but I can cut out 0.1 of here. I can cut out 1, I can cut out 2, I can cut out 3, I can cut out 5. But, 6 is the largest that I could do, but not equal to 6, and 0 is the smallest I can do, but not equal to 0. I could also write that in interval notation where I need to make sure that I don't make these brackets. Now, the question here is, if I do this and I make a box where I cut out 4-inch squares or I cut out 3-inch squared, which one of these is going to be the bigger volume? Well, let's test these out using this guy up here because this guy up here is friendly enough. For the 3-inch squares, my volume is going to be 3 times 18 minus 3 times 2, which is 6. 18 minus 6 is 12. 12 minus 2 times 3 is 6. That gives me 6. So 18 times 12 is 2. 18 times 12.
It's 216.
That's when x was 3. What about if x is 4? Okay, well, the volume is going to be x, 18 minus 8, 12 minus 8, 4 times 10 is 40 times 4 is 160. So which is larger when x is 3? Optimization problems. Will you see one this chaotic on an AP Precalculus exam? No. No. I mean, this ended up being a cubic. We don't see cubics a ton, but we see them. It's just, don't be surprised if you see a problem like this in the future. You never know with AP. You never know. All right. Now I think it's calculator stuff. So if I move my face, yeah, there's calculators for all of them. All right. What sequence of transformations would turn f of x into g of x? Okay, so what it looks like I'm doing is the difference between f of x and g of x is I'm not multiplying f of g to anything, thank God. But what I'm doing is I went from x being plus 7 to x being plus 1, which means I have a minus 6 next to x. Now, when minus 6 is next to x, that means I move right, or a horizontal phase shift of 6. I also go from -3 over here. Remember, when the number's off to the side and has nothing to do with x, I'm going from -3 to 4, so that means I'm going up 7. So a vertical phase shift of 7, okay? Not so bad. By the way, when I create these problems, I only wanted to use a calculator for this one. If this is a calculator section on an open-ended problem and you're allowed to use the calculator for this whole thing, graph that and see what happens. All right, find the domain of g of x. All right, the domain of g of x is what x values am I not allowed to use? Well, I have a fraction. And in my fraction, the denominator is x plus 1. I'm not allowed to plug in -1 because that would make the whole thing undefined. So x cannot be -1. So I'll write that out as everything from -infinity to -1 union, and from -1 to positive infinity. Okay, or you can write it out as all real numbers except x equals -1, or x cannot equal -1, or whatever. Find all zeros for f of x. All right, f of x, when you are given a rational function, f of x, the way you find the zeros is you set the numerator equal to 0. Okay, well, my numerator doesn't have a lot of stuff going on. So what I can do two things. Let's do this. Let's make life a little easier. Let's say 0 equals 5 over x plus 7. Okay? Minus 3. If I add 3 to both sides, I now have this. Okay? Multiply both sides by x plus 7. That requires me to distribute, so 3x plus 21 equals 5. Subtract 21, subtract 21. 3x is going to equal negative 16. Divide by 3, divide by 3. 5 and a 0.3 repeating, negative 5.3 repeating, or something like that. The other way to do this was you combine fractions and then set the denominator, the numerator equal to 0. That would work. I think you'd end up with the same thing anyway. With this one, I'm going to split screen, not split screen. I'm going to put in what I did on the calculator, show you what I did, come back out, we'll write out the answer. All right, for this guy, we already have a bunch of stuff going on, and what I'm being asked to do for part D is set f of x equal to g of x and solve. So this is what I'm going to do. I'm going to pretend that this is a system of equations, and I'm going to go to y equals and graph f of x in y1 and graph g of x in y2. Now, I'm going to graph this in the way that these were given to me. I'm not going to go up somewhere on the slide where I kind of simplified and combined fractions. I'm not going to do that, although I could. I won't. I'm going with the original because what if, God forbid, this is like an open-ended problem and I accidentally got one of those guys wrong? I would get this one wrong too. So I'm going with the original. So I'm typing out f of x and y sub 1. Okay, f of x was 5 over x plus 7 minus 3. So the way I do the 5 over x plus 7 is I'm going to create this big fraction. I'm going to do 5, and since 5 is the only 3 in the numerator, I could just go right to there, over parentheses x plus 7. Now, I've always been super paranoid with fractions on the TI-84 pluses. I don't know why, it's just my thing. I just wrap the whole thing in parentheses because why not? It doesn't hurt me. Okay, physically. Now there is my 5 over x plus 7 minus 3. If you were to rewind or fast forward, you can see that. Now I'm going to type out g of x, which is 5 over x plus 1 plus 4. So I'm going to parentheses. Since 5 is the only thing in the numerator, I don't need to parentheses that, divided by x plus 1. So x plus 1, close it, and then plus 4, now that my fraction is done. Okay, what this is going to allow me to do if I hit graph is it's going to give me both graphs the way they originally look, and both graphs, and if I'm using the color edition, you know, I realize most schools don't have the color edition. In this case, I see both colors for the different ones. So f of x, I believe, was blue, and g of x, I believe, was red. Now I'm solving. When you solve a system of equations, which is what I did by typing out two different equations, I care where they intersect. They intersect here and they intersect here. So I only want the x values when I solve for x. So this is what I'm going to do. I'm going to find where they intersect here first, and I'm going to do that by hitting second trace and go down the intersect, or I'll just hit 5 in this case. Now, if I'm looking for that intersection point, I'm going to move my cursor to the left of the intersection point. As Cupid Shuffle would say, to the left, or in this case, maybe cubic shuffle. Anyway, my cursor is to the left of my intersection. I'm going to hit enter. Those of us who remember doing zeros in previous videos, this is very similar. Now the second curve, I'm going to move to the right, and it shows me the second curve, and it gives me, once I hit enter, it doesn't actually show me the interval, but right now I have a dot here and a dot here, and my intersection needs to be in between. So if I hit enter, it gives me the intersection of negative 6 point blah, 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 blah. This is precalculus. So I'm going to make sure I have 3 decimals and 0.1712 rounds to 0.171. So my first 0 is negative 6.171. What about y? What about y? I'm being asked to solve for x. I'm not being asked to solve for y. So let's find the other one. Same process. Second, calc. I want to go to intersect. I care about where they intersect here, so let's move to the right a little bit. Hit enter. Now it shows up on the other curve. Let's move to the right a little bit until it crosses where they intersect. So that looks good to me. My 2 dots are blinking and my intersection has to be in between both of those blinking dots, which it appears to be. If I hit enter, I get 1 point blah, blah, or I'm sorry, negative 1 point blah, 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 blah. Okay, and it appears to be negative 1.82875. So that'll round to negative 1.821. So those are my 2 zeros. Okay, those are my 2, I shouldn't say zeros, those are my 2 x values. Okay, negative 6.171 and negative 1.821. Okay. So we got x equals negative 6.171 and negative 1.821. All right. All right. All right. All right. All right. All right, partner. Limp Bizkit. What x values cannot exist in the domain of f of x? All right, this is friendly enough. This is fancy talk for saying, what are you not allowed to plug in? I am, for f of x, right? I am not allowed to plug in 0. I am not allowed to plug in the opposite of x minus 4, and I'm not allowed to plug in the opposite of x minus 5. Friendly. Use a graphing calculator. There you go. Use a graphing calculator to find the zeros of g of x. Be right back. All right, for part B here, I'm being asked to use a graphing calculator to find the zeros of g of x. So let's go to y equals and type out g of x. X is my button right there. To the 4th, make sure I go to the right to get out of the exponent, minus 6x cubed. You could do cube by doing math 3, or you could do to the 3rd, move to the right, plus 17x, there's my x squared button, minus 54x plus 72. Let me just double check, make sure I didn't make any typos, because that would derail the entire problem. I'm good. Let's graph. All right, now this is a quartic. I'm expecting it to hit my x-axis 4 times because it's a quartic. When I go to graph, it doesn't look like a quartic. So let me zoom out to make sure I'm not missing anything. So if I hit zoom out, okay, and hit enter, I am not missing anything. So what's going on here? Remember, with quartics, you can have 0 real solutions, you can have 2 real solutions, or you can have 4 real solutions. Remember, there's complex solutions. So for something like this, I could have no real solutions and have 4 complex solutions. With this, it looks like, and I'm going to zoom back to normal, so zoom 6 gets me back to normal. With this, it looks like I have 2 real solutions and 2 complex solutions. So all I have to do is find the 2 zeros. So let's do that. Let's hit second, trace, takes me to calc. My job is to find the zeros, so I can go down to 2 and hit enter, or I can just hit 2. Left bound, whenever I do this, it automatically places me at 0, so I need to go to the right a little bit until I see that little blinky cursor. There you are. Keep the left bound to the left of the 0, which it is. Hit enter, cross the x-axis, hit enter, and it's telling me in that little tiny interval right there is where my 0 exists, and it does. Let's hit enter, and I get a lovely 2. How about that? You wouldn't think, but I do get a lovely 2. So if that's 1, 2, is this going to be a lovely 4? I don't know. Let's hit second, trace to get my other 0. Go down to 2 to hit 0. Move to the right so that you're now to the left of this other 0. I just like seeing it, so hold on, there it is. So now I'm to the left of my 0, hit enter. Move to the right of my 0, hit enter. It's hard to see, but my 0 lives in between this little interval, and I do get a lovely 4. So my 2 zeros in this case are regular 2, regular 4, and I'm going to have 2 complex zeros that I really don't care about for the case of this problem. And I'm back. So the zeros ended up being very friendly. X equals 2 and 4. Remember the word that I was trying to think of a couple minutes ago and I struggled so badly? There it is. I knew it would show up. There it is. And I didn't cheat, I swear. All right, for C here, I looked at this and I think I made a typo somewhere. So I'm going to change this. I'm going to get rid of this part to it. Okay? I'm going to just change it because there's a typo there. I don't know what I did wrong. I did something stupid. It happens from time to time. F of x has 3 distinct zeros. Here's the thing. We don't know what A is. So A has to be different from -2 and -4. Okay, so A cannot be -2, A cannot be -4. Great. None of those, I'm ignoring this part, none of those values are a 0 of g of x. The zeros of g of x ended up being 2 and 4. So, okay, find a possible value for integer a if a is -12 and +12 in between them. I could use 5. Okay, so that would still, no, I can't use 5. I can't use 5 because of that. I can't use 4, and I know that already. I can't use 0, so let's use 7. 7 will let this work out where if I put 7 right there, if A is 7, I now have a 0 of -7, which has nothing to do with any of these, nothing to do with any of these. Nothing's going to disappear. Nothing's going to go away. Let's just stick with 7. I like it. I hated this problem that I created, although it's very similar to a problem you might see in the future. I just didn't like it. Just didn't pan out for me. So I'm going to face again. All right, now we're only using a graphing calculator, I believe, for just B. Right now, for A, we are finding an appropriate model for f of x and g of x. So we're going to look at each of these and see if it's linear, see if it's quadratic, see if it's cubic, whatever. F of x, I seem to go down by 1, go up by 1, so it's not linear, go up by 3, go up by 5. So it's not linear. Let's test to see if it's quadratic. Go up by 2, go up by 2, go up by 2. F of x is quadratic degree 2. Let's see what g of x is. Okay, g of x, I go up by 4, go up by 4, go up by 4, go up by 4 is linear. Now that I know that f of x is quadratic and g of x is linear, I could use a graphing calculator to find the equations for f of x and g of x. Be right back. Okay, well, we just found out that f of x is quadratic, and now we need to find the equation. So let's hit stat, let's hit edit, and let's type in those values. 1, enter 2. I can just use my calculator or my keyboard for this one. Don't need the calculator. Now, if you're on a keyboard, 0 is fine, but keep in mind that the negative and minus signs are different. So you're going to want to type out -1, again, the stupidest thing that Texas Instruments has ever done. 0, what else do we have? 3, 8. Okay. Let's quit out of this second mode. This one's the quadratic, so I'm going to go to stat. I'm going to go to edit. And I'm going to go to calc, and I'm going to go to quad reg, and I'm going to hit enter, 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 and then finally enter on calculate, and it gives me a lovely quadratic equation of y equals 1x squared minus 4x plus 3. So I'm going to write out y equals x squared minus 4x plus 3. Now on to the linear. If I want to clear everything out, 2 plus 712 does the job. Just don't do this on a personal calculator if you have stuff saved. Go to stat, edit. I got 1, 2, 3, 4, 5. So 1, enter 2, enter 3, enter 4, enter 5, enter. I've got 5, enter, 9, enter, 13, enter, 17, enter, 21. Don't have to worry about negatives there. Second mode. Stat, Calc, Linreg. So hit 4, hit enter a bunch of times, and this calculates out to y equals 4x minus 1.4. Okay? All right, so f of x ended up being, I have it written down, x squared minus 4x plus 3, and g of x ended up being 4x. I'm looking at the wrong thing. Minus 1.4. That's why I said point. All right. Find the quotient. No calculator. Great. G of x over f of x. So we're going to need to use polynomial long division. So x squared minus 4x plus 3. That point there is just going to be a pain, a thorn in my side. Again, I create these problems and I don't always create the best ones. But if you can figure it out, you're in great shape. 4x times what gives you regular x to the fourth? 1/4 x does that. All right, so 1/4 x times 4x gets me x squared. 1/4 x times negative 1.4. Negative 1.4 divided by 4.
It's negative 0.35.
You would never be asked to do that on a no calculator section, so I'm okay with cheating just a little bit. Flip the signs, cross u out, you become negative 3.65x plus 3. 4 times what gets me negative 3.5x. Negative 3.65 divided by 4 is?
The answer is negative 0.9125.
Negative 0.9125 x. Nope, just that. So that gets me negative 3.65x. Negative 0.9125 times negative 1.4.
It's 1.2775.
1.2775. Cross you out. Make you a minus. 3.12775. 3 minus 1.2775.
It's 1.7225.
So I would put that, my remainder, right up here. And the factor that I use to divide right here. Again, would you see something this crazy on a no calculator section? Absolutely not. But again, you know, sometimes the nice thing about these videos is if I do a bit too much and you're like, I get it. I don't like it, but I get it. Life is easy. Speaking of life is easy, this one should be a whole lot friendlier. Now, what I need to do is I need to find out what g of 8 is. Okay, well, this guy is linear. I also have a calculator. I also have these equations, and I might use that, but I don't think I really want to. In fact, I know I don't want to. G of 8, if you are 6, 7, 8, all I'm doing is adding 4 every time. So you become 25, you become 29, and G of 8 is 33. Minus f of negative 2. So 0, negative 1, negative 2. This is quadratic, so we should be able to see the pattern. Since this since it bottoms out at negative 1 and goes to 0, I know you are going to be 3. You are going to be 8, and I'm going to add 5 plus 2 more, and 5 plus 2 is 7. 7 plus 8 is 15. Okay, and that continues the pattern. All right, so regular 15. And 33 minus regular 15 is 18. I think this whole thing uses, if I recall, this whole thing uses my graphing calculator. So let's read through the problem. During a severe rainstorm, water collects in a rain gauge. The gauge is empty at the very beginning, okay? And the amount of water follows a linear pattern up until 20 minutes. After 20 minutes, it is now quadratic. The rainstorm stops after 60 minutes. Selected values of A of t, cubic centimeters of water, in the gauge are shown below. Okay, so up until 20, it's linear. And after 20 to when it stops, which is going to be 60 minutes, it's quadratic. So I need to make a piecewise function where up to 20, I get linear. And after 20, or between 20 and 60, I get something that's quadratic. That requires a graphing calculator. I'm going to use a graphing calculator. Be right back. Well, this isn't going to be fun at all. So let's start out with the piecewise function. We are told that our data all the way up until when t is 20, we're told that it's linear. So this is what I know. I'm going to use linear regression, even though it may not be necessary. It's giving me the calculator. I'm going to show you how it's done because more money for me if I take more time to do this stuff. So I'm going to hit stat, edit. Okay, it tells me in the word problem that there's no rain at the beginning. So when time is 0, the rain amount is also 0. I also know that at 20, okay, when time is 20, my rain is 40 cubic centimeters or whatever unit that we used, right? I'm looking at the tree at 40. So 40, enter. Now, these are the 2 points that we know. That's it. Only those 2. But that's all we need. You only need 2 points to do lin reg. So if I quit out of this, if I go to second stat, or just regular stat, I don't know why I did that. Regular stat, hit regular stat, go right to calc and go to lin reg, and hit enter a bunch of times until you get calculate, it gives you a lovely function of y equals 2x plus 0, and we will write out the equation a of t equals 2 of t, and we care about when t is less than 20, okay? Or I guess maybe in this case we could do less than or equal to 20. So that's part 1 of the piecewise function, okay? Set that aside, remember it, memorize it, because now we need to do the part that's quadratic. What I know about quadratic is at 20, it starts quadratic. So we could use that same point. So let's quit, right? Let's clear everything, because I do like to clear everything. It just makes life easier. Second plus 7, 1, 2. Go to stat, okay? Go to edit, and we're starting over. The point 20, 40 is still part of our quadratic. So we'll hit 20, and I'll get to 40 in a second. We also know that 30 is part of it. We also know that 40 is part of it. And we can move to the right and know that we can use 40, 50, 80. Okay? We know this is going to be quadratic. So let's quit by doing second mode. Let's go to stat. Let's go to calc. Let's go to quad reg, which is 5. Hit enter a bunch of times until you get to calculate and hit enter again. And it gives us an okay looking formula. Y equals 0.1 x squared minus 4x plus 8. So when I write this out on paper or choose a selection from multiple choice, I'm going to make sure I choose the one that says A of t equals 0.1 or 1/10 t squared minus 4t plus 80. Okay, and this matters between 20 and 60. Why 20 and 60? Because the rain stops at 60. So that's it. So write out your piecewise function now. All right, so Knowing that my graphing calculator gave me a bunch of x's and stuff like that, I'm going to use a of t. The first part is linear. That ended up being just 2x, so 2t, where t has to be between 0 and 20. Okay. The second part was quadratic. A of t. Okay, our calculator said something to the effect of 1/10 x squared, so I'll make it t squared. Okay, minus 4x, so I'll make it 4t, plus 80. And that is from 20 all the way up until 60. And you know what? I can throw an or equal to there. It doesn't really matter where it begins. You're allowed to do that. That's my piecewise function. Now what I need to do is find out how long it'll take to reach 100 centimeters. Well, I don't see 100 centimeters, cubic centimeters. I don't see 100 cubic centimeters anywhere on this chart, but I do know it happens after 40, which means I need to use my quadratic portion to find that out. So I'm going to pretend a of t is 100, and I'm going to I'm going to graph this guy right here and 100 in my graphing calculator. Let's see what I get. All right, so for part B here, what I'm supposed to do is find out how long it'll take to reach 100 centimeters. So if I'm looking at my piecewise function, or better yet, if I'm looking at the table, it tells me that at some point after 40 seconds, that's when my amount is going to hit 100. So what I'm going to do is I'm going to set this equal to, the equation 0.1. And instead of t squared, I'm going to hit x squared. So x squared minus 4x plus 80. And then I'm going to go down here and I'm going to replace whatever with 100. Now, you could do this just by solving a regular old equation. You could say 100 equals 0.1 x squared minus 4x plus 80. And yeah, you're going to have to use your calculator at some point. But this is much, much, much friendlier. And you're going to want to use it this way because that's going to be a nightmare. So I have my equation right there. I have my 100 value right there. Let's hit graph, and I'm expecting to only see one of them. And it looks like in this case, I'm expecting to see neither of them. Here's why. My picture goes out to the tens, and one of my numbers is 100. See that 80 there? That 80 makes things explode way up the y-axis. So what I need to do is maybe I zoom out to find a better window to use. So I'm going to hit enter on zoom out, and I'm given nothing. So let's zoom out again. There you go. So if you want to, you can go over here and fix the window, and maybe I'll do that. Maybe I'll fix the window from negative 160 to, I'll delete, make that 70. And that's the x value, actually, not the y value. That's the x value. I'm going to make you 0. And if you're wondering, whoa, why are you doing that? I thought I saw something on the left side of the y-axis. A negative x implies a negative t, and a negative t implies time travel, and we're not doing that in precalculus. My y minimum, I'm going to start at 80. And if we hit graph, things are a little bit nicer. Now, I only care about that value right there. Again, I know that this goes over here, but I'm not going to care about the value in negative land because negative land implies time travel. Going back in time can't do that. This is not Back to the Future. So I care about my intersection. Second, trace, hit 5 for intersect. The first curve, it shows up automatically at 80. My x is 80. So I don't want 80. That's a lot. So if I hit negative, there you are. Okay. So if I hit enter on that, hit enter on this, and hit enter on that, it's going to take 44.4948, blah, 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 blah. If I round this to 3 decimal places, 44.495. Now, this is a time value, and I care about seconds in this problem. So when I solve this, I'm going to make sure I put 44.9495 seconds. That's my guy. And it's not pleasant. I believe in the video I accidentally said seconds, but it's actually 4.495 minutes, not seconds. If I said seconds, I'm sorry. I'll try to edit that if I remember to edit it out. This video is getting out of hand. Predict the amount of rain when the storm stops. When does the storm stop? At 60 minutes. So all I have to do is find out what happens at 60. Take it away. All right, so for part C here, I'm being given information that I'm supposed to plug in some number, okay? It tells me when it stops raining. I kept my original equation there. I got rid of the 100, don't need it anymore. I care about when it stops raining. When does it stop raining? When time is 60 minutes. So I'm going to make sure that I keep this up here and find out when X, I know it's T, but when X is 60. What I can do is I went to graph. I went back to graph normal. That's fine. I hit zoom 6. If you go to zoom out, I'm thinking I need to plug in 60. So why don't I do this? Why don't I go to window? And if I'm supposed to plug in X is 60, why don't I make U 70 so that I have a graph? If you're wondering, like, why do you need to do this if you're just going to plug in 60? You don't even see anything. No, and I really don't care. You can't plug in, you can't do this, which is second calc, value. You can't do this unless the number you plug in is visible on the coordinate plane. So if I do second trace value and type out 60, I get a cool 200. Even though I don't see the graph, I see what I see, and what I see, I don't know why I talk like that. What I see is a nice 200. So 200 cubic centimeters, let's go with it. Oh, look at that. 200 cubic centimeters. The rainwater is so 200 cubic centimeters is transferred to a cylindrical container with a radius of 7.5 centimeters. Cylinder. So the volume of a cylinder is pi r squared h. What do I know? I know the radius is 7.5, and I know the volume is already 200. So 200 is going to equal pi 7.5 squared h. So in order to do this, I have to divide both sides by pi 7.5 squared, cross u out, divide both sides by pi 7.5 squared, and I think this requires a graphing calculator. Okay, so I did a little bit of math, and right now what I need to do is find out what 200 divided by pi 7.5 squared is. So I'm going to make sure I keep pi, which is second caret looking thing, times 7.5 squared. I'm going to keep that in parentheses because I get super paranoid when it comes to fractions on these calculators. Hit enter, and you get 1.1317 blah, 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 which simplifies, if we're using pre-calc rules, to 1.132 centimeters. That's my answer. And it did. And so the minimum height of the container is we need a container that is at least 1.132 centimeters tall. So kind of not a, you're looking at this super wide container, not tall at all. That's what you get. I mean, also that's what you get when I have to create these problems. You're just going to get what you get. Don't expect perfection. That's for Jesus. What type of model is most appropriate for the data? No calculator needed for this one. In fact, the only time I believe I'm going to use a calculator is for B and D. The table on the right shows the data of a ball thrown in the air when the ball is y feet in the air after x seconds. So what can we imply from this? All right, well, you're standing 18 feet in the air when the ball is thrown, and then it goes up, then it goes up, then it goes up, then it goes up, then it goes down, 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 down. And this doesn't even make sense because this implies negative. I wonder if that's going to show up later. Okay. What type of model is most appropriate for the demonstration to demonstrate the data? I probably already know, but let's just do it anyway. I mean, if you throw a ball up in the air and comes up and comes down, there's really only one. So what did I do? I added 14. I added 10. I added 6. I added 2. I subtract 2. I subtract 6. I subtract 10. I subtract 14. I subtract 18. It is not linear. Is it quadratic? Plus 4. Minus 4, minus 4, minus 4, minus 4, minus 4, minus 4, minus 4. It's quadratic. So let's take this information. Let's plug it all in. Oh my gosh, quadration? That's what happens when I talk and write at the same time. I'm not a wordsmith. It's quadratic. Find the equation for the data. Calculator. All right, we're almost at the end. We know we have a quadratic function, so let's go to stat, let's go to edit, and let's plug it all in. 0, 1, 2. Yes, I'm typing in all of my numbers. I'm typing them all in because I'm a math teacher and precision is key. All right, 18, 32, 42, 48, 50. Feel free to fast forward this, or while you're waiting, you click the like and subscribe button, please. What is it? 7 is 32. 8 is 18. 0. And the opposite of the Taylor Swift special is negative 22. And of course, I can't type in negative because it scares TI 84 pluses, even the color editions. All right, there we have it. I know we have a quadratic. Let's quit. Let's go to stat. Let's go to calc. And let's go to quad reg, which is 5. Okay, enter, 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 enter. Y equals ax squared plus bx plus c, where a is negative 2, b is 16, and c is 18. So y equals negative 2x squared plus 16x plus 18. Fun. Cool. So the equation that I found was, and it's y and x, so y equals negative 2x squared plus 16x plus 18. Great. What is the domain? What am I allowed to plug in? Well, I can't go back in time, so 0 is the smallest amount, and I can actually bracket that off because I can include 0. But what we found out is that after 9 seconds, I hit the ground. So 9 is the largest because once I go beyond 9, I hit negative land. Okay, so the only numbers that I can plug in are between 0 and 9, including those numbers. That's my domain, the numbers I'm allowed to plug in. Anything smaller than 0 means I did something back in the past, and anything bigger than 9 means it goes through the ground. Okay, we're talking about a ball here. All right, what is the ball, or where is the ball after 5.618 seconds? That requires a graphing calculator. All right, last calculator opportunity for this one. Where is the ball at 5.61 seconds? I didn't keep my equation. In fact, I deleted everything. There is a way that if you were to go here, you can have this show up in y sub 1. I think if I go to second list, no, not worth it. 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 No, yeah, not worth it. I'll just type it out. There's a way that you could do this, but I'm not going to do it. Negative 2x squared plus 16x plus 18. If I hit the graph button, maybe I'll see a parabola. Yeah, I probably will because it's skinny. There it is. I care about where the ball is at 5.616. Unlike a previous problem, I can actually plug in 5.616 right now at this very moment. So I'll hit second, trace, value, and I'll type out 5.618. Did I keep saying 616? I think I did. 618 is what I want. That is what I want, 4.7641, which simplifies to 4.765. And that'll do it. 34.464 feet. Oh man, I hope I don't do this problem and a bunch of golfers hear me. That's 764 feet. That's what I get. Just way off today. Going off the rails. Off the rails at the very end. Find the average rate of change on 2, 4. Now, before you're like, ugh, it's not that bad. 2 is A, so I'll call you A, which means I'll call you f of A. 4 is B, so I'll call you B, and I'll call you f of B. F of B minus f of A over B minus A is going to be 50 minus 42 over 4 minus 2. 8 over 2 is 4. The average rate of change is 4 feet per second. So that's Precalculus. Watch all my other videos. Watch everything. Like and subscribe. Tell your friends, tell your family, tell your kids, tell your wife, tell your husband too, because they're telling everybody out there. Thanks for watching. Love you all. Bye.